ये 2 लोग ज्वाइन करके हैं ना। करते रहेंगे। मैडम को एक बार बात करता हूँ मैं। हाँ हाँ। हाँ, ठीक ठीक ठीक। एक बार कंफर्म कर लेते हैं ना। हाँ हाँ। सेशन 3 में आपके विवेक सर ही है ना।
इस आदरी की
ठीक।
नहीं आए दिन करेंगे सर आए दिन मार काटो
creeper is so cute, especially for inspiration. The creeper, which is very common. The middle space
Hello, Vivek sir, am I audible?
Yes, sir. Good evening, Professor Vivek. I think our speaker for session 3 has joined the meeting. But he is not responding, sir. Lal Pratap, sir.
Yes,
I
ma'am.
can see Vivek Kumar, sir, in the meeting, but he's not responding. So,
Arvind sir is trying to contact.
okay. Once he confirm that his presence, then we will start the session, I guess.
Oh, okay, ma'am. Okay. Wait
Okay,
for a
sir.
few minutes.
Yes, sir. So, good evening, dear participants. I hope you enjoyed yesterday's sessions. So, if you want to share your some feedback or you want to say something, dear participants, you can share your views. If anybody from the participants. Meanwhile, we are waiting for our speaker. You can say if you want to share anything.
Hello.
Yes, sir. Yes, Professor Bohra. Good evening, sir.
There is some technical glitch at the part of Vivek sir, so he is trying to address. Please wait.
Why it's not able to detect the speaker? I don't get it.
Vivek sir, now you can check.
Yeah, now I'm able to hear.
Okay, sir.
So am I audible?
Yes,
Yes,
sir.
sir,
Properly
you are
audible.
clearly audible.
But I think there was some problem. I don't know what. I was not able to hear you guys.
Now you
Uh,
are audible, sir.
Okay, just give me a second. Okay.
yeah,
Okay, sir.
sure, sir, sure.
So my voice is clear?
Yes, sir, it is clear. Can you please turn on your camera also so that
Yeah,
our
just
audience can see?
just give me a second.
Yeah.
Is it okay now?
Yes, sir. Now you are visible and your voice is audible
I
to
think
us.
there's some problem. I don't know whether this headphone, the Bluetooth headphone is not working or something like that. Maybe that might be an issue.
Yes, sir.
Anyways, so let me share the screen if that works for you.
Yes, sir. Sure, sir.
So can you make me a host or something? Do I need to be a host to share the screen, or
Yes,
is it?
You are
you are
having the
already
control,
a
sir.
presenter, sir. You can share your
Okay.
screen.
Okay, got it. Just give me a second. Is it visible?
Yes, sir.
Yes, it is.
Okay. Is it full screen or is it half screen or something like that?
It is in edit mode, not full screen. You
Okay,
can
that-
make it a slideshow.
Okay, I've already made it as a slide. So what about this? Is it still full screen or not?
Not.
Okay, I think now I need to share the whole screen. That's the problem sometimes what I see. Just give me a second. I think I need to.
So meanwhile, sir, you are checking your connection. Shall I introduce you to the audience?
Yeah,
If
sure.
you allow.
Yeah,
So,
absolutely.
dear participants, let me introduce you with today's speaker. This is Professor Dr. Vivek Ashok Bohra with us, and I'm very delighted to share his profile. I'm overwhelmed. Actually, I'm overwhelmed. He has received the PhD from Nanyang Technological University, Singapore in 2011. And then from 2011 to 2013, he was postdoctoral researcher at Marie Curie Fellowship in ESAE Paris University, Paris East. And then in 2013, he joined IIIT Delhi, India, where he is currently Professor EC and Dean, Innovation Research and Development. He has authored and co-authored over 100 publications, journals, referred international conferences, book chapters, and he is also having 5 patents. So Professor Bohra also supervises the Virocom Research Lab at IIIT Delhi, and he is co-founding faculty member for Li-Fi Center of Excellence at IIIT Delhi. And from Feb 2023, he is also a recipient of TIH IoT Chanakya Faculty Fellowship from TIH Foundation at IIT Bombay. I'm totally overwhelmed. Just before the commencement of this session, I was just talking to Lal Pratap sir that I am willing to join as an intern in your Center of Excellence. If you would allow, if you would allow.
No, I think you're most welcome to come to IIIT and work with me. That's not a problem. And so all of you, in fact, are welcome to have a discussion on me, what sort of work I'm doing at IIIT Delhi. And
Yes,
feel
sir.
free to drop me an email and we can obviously have a discussion on how to take this forward.
Yes, sir. It's my humble request to you that if convenient to you, can you please share your contact details with me and with all the participants? We would like to grab this
Yeah.
opportunity.
Sure. It will be my pleasure. So email ID, if you want, I can share it at the end. So it's
Sure.
vivek.b@triple-it.d.act.in, and I think you can just type my name in Google. I think it automatically will show you all the details. You don't need to search very hard.
Of course, sir. We can search for your details, but seeking your permission and being legitimate, I think it's more important. That why
No, it's okay. It's okay. No
we are
issues.
contacting you.
No issues. No issues from
On
my
a
side.
behalf, sir, on a behalf of entire organizing committee, on the behalf of our institution, and on the behalf of all the participants, I'm highly grateful to you that you have spared your time and you are with us for this session. So thank you so much, sir. And please,
No
now the
issues.
audience is all yours. Please start the session.
Okay, thanks a lot for the nice introduction, and thanks for the invite. And it's my pleasure to speak at this AICT FDP on IoT and intelligent systems, next generation communication and artificial intelligence. So as mentioned already, so I'm Vivek. I'm currently working as a professor in IIIT Delhi. So first of all, I'd like to thank the organizers for such a wonderful FDP, and I hope I can contribute in a meaningful way in the discussion that has happened so far. And my topic is next generation vehicular communications. And so we already have a lot of techniques that are available for vehicular communication, starting with DSRC, dedicated short range communication, V2X to cellular V2X, VLC V2X, RIS V2X, solar V2X. And in fact, we have been working on V2X for some time now. So V2X is one of the areas that we're working on. Apart from that, we have been exploring a lot of other areas as far as Li-Fi, as well as solar communication, other areas are concerned. So without any further delay, I will just start with the presentation. So please let me know if the slides are not moving or something. If I get stuck somewhere, or in case the screen is not visible, please feel free to interrupt me. And in case if you have some doubts, some queries, some concerns, some suggestions, again, feel free to interrupt me. I would prefer it to be a more of an interactive session, and please feel free to stop me whenever you feel like doing so. Okay. So this is the agenda: introduction to wireless cellular standards. I think everybody knows what is wireless cellular standards. This talk is about communication and IoT. So I think most of people would be already have been some sort of information on what is wireless cellular standards, what is why vehicular communication, current vehicular communication standards, vehicular visible light communication, RIS assisted vehicular communication, fiber wireless and digital twin based vehicular to infrastructure network, and some sort of future directions. Before I start with actual talks, just wanted to give a brief overview for the interest of the audience about my research group, what we have been currently working on. So as mentioned, I'm leading the IIIT Delhi Wiracom research group, and we have multiple projects on different wireless areas. They talk about visible light communication, vehicular communication. Yep. Hybrid Wi-Fi networks, underwater communication, UAV assisted communication, solar communication, and anything to deal with communication. We have been working on it to be more brief in that case. And we have a lot of sponsored projects from Ministry of Education through Spark, or Ministry of Electronics and Information Technology, or DST, or Department of Telecommunication as well. And we have a team of around 30 plus researchers, including 10 PhD, MTechs, BTechs, who have been working in this area. And we have quite a good amount of publication in this area. In addition to this, I'm also a co-founder for Center of Excellence on Light Fidelity, and this is some areas what we are working on. We have already shown practical demonstrations using light as a means of communication, and we have already organized multiple workshops, talks, filed numerous patents, and also we have developed technology transfer as well as the hardware, where we have shown practically how light can help in communication, how solar panels can help in communication, and all these things as well. So if you're interested to work on these two areas, please feel free to drop me an email. In addition, I'm also doing some sort of NPTEL SWAM courses. So there are 3 different courses that I've been taking for NPTEL SWAM, and all these 3 courses have deliberately kept in Hindi language to have a mass outer reach. So typically for India, rural areas and a lot of areas, we doesn't have English as an official language. So these sort of courses will be helpful. So I have taken 3 different courses. One is the fundamentals of wireless communication. This is the first course that I offered. Then depending upon the responses received, and again, I offered another one that is advanced topics in wireless communication. And again, this one is also in Hindi. And in addition to this, I am currently offering this course, Enabling Technologies for 6G Communication Networks. Again, this is also in Hindi. And this will be offered from February this year onwards. So these 3 courses completely covers wireless from fundamentals to advanced techniques of wireless, including some of the technologies that are going to be the part of the 6G cellular standards. In addition, I'm also offering one Swayam Prabha course that is direct to home in channel number 18 from IIT Bombay, Electronics and Communication Engineering. So this is something about my background and what sort of work I do, what sort of courses I take, and all these things. Now, coming back to the actual talk on the topic of vehicular communication. So before I start with the vehicular communication, just to give a hint of what is the cellular standards. I think so 5G, I think before 5G, everything was focused primarily on. So before 5G, I think everything was focused on enhanced mobile broadband. So if you remember the era of COVID or after that, so everybody was hooked to the internet either through online classes or having video calls or something like that, thanks to 4G services and the Wi-Fi services. So even being indoors, you were able to communicate to your family members or play games and all these things thanks to the focus on the mobile broadband in 4G and other standards. From 5G, the focus has shifted a bit. So in 5G, the focus is not only about enhanced mobile broadband. There are two more verticals that were added in 5G. One is a URLLC, ultra reliable low latency communication, typically to facilitate robotic surgery, tactile internet, and all these things. And in addition, there was another vertical that was added, that is massive machine type communication. This is to facilitate IoT sort of a connectivity where you can connect massive number of devices through 5G networks. So these two verticals were additionally added on top of enhanced mobile broadband, so that it completes the triangle. So instead of focusing only on one use cases, these two additional use cases were also added depending upon what sort of applications you are targeting. Going forward, beyond 5G, we'll focus on enhancement of this enhanced mobile broadband plus, URLLC plus, and massive machine type communication plus. So this is additional evolution that you will see for beyond 5G systems. And again, there are a lot of talk in the town about 6G. So going forward, 6G will also have multiple verticals. Like we have verticals in the sense of it will not only focus on the cellular connectivity, but also human, not only focus about human connectivity, but device connectivity, and how intelligence and AI and ML can play a role in some sort of learning and optimization of the network. So going forward, we'll see a lot of other advancement in the wireless communication era, and how the sort of learning algorithm or localization or precision or integrated and sensing and communication is going to play a role in the next generation of cellular standards. So going forward, we're going to see a lot of excitement, a lot of new techniques that may come up as a part of the 6G communication networks. So just to give an example of 5G use cases, so depending upon what sort of use cases you're targeting, either mobile broadband or augmented reality, self-driving car, or smart home building. So you are basically intersection of in one of the three verticals. If you're just focusing on gigabits per second, basically you're focusing on one vertical. If you're focusing on mission critical applications, when you're focusing on self-driving car, basically you're focusing on ultra reliable low latency communication. And if you're focusing on smart city sort of application, you're focusing on massive machine type communication. But there's some application which intersects on all these three verticals. For instance, if you're focusing on smart home building, that may require enhanced mobile broadband, and they may also require massive machine type communication. So there's some applications which are intersection of these three verticals. And as you know already that in India, I think we have already installed more than 3 to 4 lakhs base stations, 5G enabled base stations. And there is some sort of exponential growth in terms of number of base stations that have been deployed as far as 5G is concerned. So there are some logical reasons why 5G is important, obviously. So 5G, as I mentioned, it's not only about enhanced mobile broadband. There are two more verticals added to it. And in terms of it, so there are a lot of low latency applications that might pop up in next few phases that will require some sort of 5G services. And obviously, autonomous vehicle, there's a lot of impetus from government side on autonomous vehicles, specifically not autonomous e-vehicles, but going forward, we may see some sort of autonomous vehicles as well that will require some sort of 5G enabled services as well. And in addition to that, there are wearable devices, intelligent transportation system, robotic surgery, or remote surgery that will require some sort of 5G use cases. So going forward, again, we are going to see next 10 years down the line, or now only 6 years down the line, by 2030, the first set of standards for 6G also. The work has already started to design or work on the 6G specifications. And a lot of, if you are aware, a lot of academic institutions as well as industry professionals are working towards what sort of technology will be part of the next generation of 6G cellular standards. So this is a brief introduction about the 5G and 6G timelines. And so right now we are in era of this thing release beyond release 18 and 19. And this is basically catering for the enhanced mobile broadband and some applications of massive machine type communication. Beyond this, maybe by release 20, we'll see some sort of applications for URLC as well. And now coming back to the V2X, so there are a lot of applications for V2X. So V2X is not only about how the vehicles will be able to communicate with each other. So obviously that is one of the most crucial applications, how the vehicle will communicate with each other, how the vehicle will communicate with the infrastructure, how the vehicle will communicate with the pedestrian. But then, apart from that, there are a lot of pertinent applications that we might see for V2X in 6G specifically. So when I talk about RIS assisted edge computing, I will show one example use case of this one, how vehicle is communicating with the base station with the help of RIS, street light assisted edge computing, V2V assisted edge computing, and all this direct offloading to satellites through vehicles and ground radar based assisted satellite computing. So all these sort of applications you might see in 6G as far as vehicular communication is concerned. So this is just to build what sort of applications you may foresee in future as far as vehicular communication is concerned, or to be more specific, V2X is concerned. Now, what is the rationale behind vehicular communication? So vehicle to vehicle communication. So there are a lot of potential applications for it. Obviously, anti-collision systems, V2V information sharing on driving conditions, congestion, and optimal routes. So obviously, one of the most prominent application for vehicular communication is to avoid collision, obviously. So if you want to detect what sort of vehicle that is in front of you and that is on back of you, so obviously we'll try to avoid collisions. Specifically, there are a lot of areas, sharp turns, sharp curves, where you typically have more probability of collisions. So how will you design systems that will avoid something like this? And obviously, if on top of it, you can get some information on the congestion, optimal routes, that obviously will help you to optimize your traffic route and save a lot of time as well, save time and fuel as well. So just to give us some sort of insights on why vehicular communication is important, I think this every day in some of the other news article you read about some sort of road fatalities. When you talk about Delhi, or you talk about Jaipur, or you talk about any other city in India, typically you read a lot of, and with a lot of new highways popping in and a lot of new avenues for transport coming in. So road fatalities have also increased tremendously. So just giving us some sort of snapshot. We talk about Chennai, we talk about Tamil Nadu, we talk about Odisha, we talk about this country tops list of world's worst driver. India ranks at 4th place, and all these things. This gives you enough food for thought in the sense of it. So think about it. Why road safety is a very, very important issue. And again, on top of it, if there's a fog, obviously living in Delhi and Jaipur, you can relate to it. At least in northern India, when you see Yamuna Expressway, or even nowadays National Expressway 4, which connects in Delhi to Jaipur, a lot of accidents typically happening during the fog time and all these things. The most dangerous time to be on Delhi roads, obviously, and this is one of the issues that I thought maybe something what we can do as a team, and propose some techniques that can alleviate the problems of road safety. Again, more and more data on road safety, and number of people who are dead or injured, or a lot of economic losses because of some sort of accidents or collisions and all these things. Again, so this is the data what I've obtained from Ministry of Road Transport and Highway. I have a latest set of as well, but I want to give some sort of highlight at 2019 one. If you can see, this is something that is very, very important. As you during the COVID era, as you can see, there was some sort of decrease 2020 because number of vehicles on the road were pretty less. But again, it started picking up from 2021 and 2022. So obviously, 2020 is an anomaly in this sense of it. And in this year, you can see the number of fatalities was reduced because there were less vehicles flying on the road. And once the COVID was over, so obviously the number of vehicles have increased and number of collisions and fatalities have also increased over this year. And this data is actually for 2019. This is the latest data that I have obtained. And this also gives you a very, very important snapshot of it. And if you just compare two-wheelers with cars and taxis, so this is a confusion sort of a matrix. So when two-wheelers collides with the cars and taxis, this is the amount of accidents that typically occur. And this is the highest. If you see, this one is the highest. And typically in any column, if you see, or any row you see, if the cars are involved or low mobility vehicles are included, vehicles are involved, fatalities are typically higher. So this is something that typically can be alleviated, we believe, if appropriate warning is given to the driver and at a given point of time and at an appropriate distance. This is something that typically can be avoided by appropriate signaling mechanisms. Okay. So again, this is the data that we again obtained from 2016, but there's not a big difference from this data and recent data. There was some data that was already spoken by the Ministry of Road Transport and Highways that India is #1 in number of persons killed in road accidents. This is again something that is not to be proud of. So in absolute terms, in number of accidents, we are the third, but in number of fatalities, we are #1. Okay, and so in person injured, we are 3, but number of persons killed is still #1. So this is something that has been bothering to us for some point of some years now, and this is something that is obviously something that has to be taken care of, and some sort of techniques has to be devised or worked on so that this can be alleviated, or at least this can be minimized. You got it. So this number is not a small number as far as India is concerned. So this is again data I've obtained from other states as well. So I'm not going to details of the insights from this data. And as I mentioned, road safety is an important issue. So based on Ministry of Road Transport and Highway 2022 annual report, a total of 461,302 road accidents have been reported by states and union territories during the calendar year 2022, which claimed around 168,491 lives. This is a reported data. Just imagine how many lives were lost, which were not even reported. This is a actual reported data, but there would be, I think, 3 to 4 times more lives would have been lost. Some of the lives are not even reported in media or in other government sources. And cause injuries to around 4,43,336 persons. This marks an increase of 11.9% in accident, 9.4% in fatalities, and 15.3% in injuries compared to the previous year. India roughly accounts for just 1% of the global vehicular population. However, it accounted for about 6% of total global accidents, again 6 times as compared to the number of vehicles. In 2022, there were around 168,000 deaths due to road accidents in India. So this is something that is obviously not to be proud of. Okay, and global perspective is also not very different. It's slightly better as compared to India. If I talk about around 1.35 million people die each year as a result of road traffic crashes. Road traffic injuries are the leading cause of death among the people aged between 5 and 29 years. Road traffic crashes cost most countries 3% of their GDP. Again, apart from the fatalities and the injuries that is the leading cause from the road accidents, there is a significant economic loss associated with it. That is around 3% of the GDP. Whether you talk about insurance, whether you talk about loss of the vehicle, loss to the transport infrastructure, and obviously congestions and all these things. So again, this is something that is that has to be dealt with, and some sort of technique has to be proposed in order to alleviate this problem as far as road safety is concerned. So causes, obviously, so before going into the depth of the techniques, as a good researcher, you should always find out your motivation to work on an area and then find out the reasons for that, whatever problem or whatever issues are there, and then try to alleviate the problem. So this is a very good approach to do research. So first we find out the use case, that is there are a lot of road accident that is happening in India and abroad. And then what is the causes of this road accident? So the first cause, what we find out, again, we have got updated set of data as well. But the major cause was fault of a driver of a motor vehicle. So fault in the sense of it's maybe an unintentional fault. Maybe some drivers may doze off, or somebody is over speeding, or maybe drunk, or whatever it is. There may be, but maximum results or maximum accidents are caused by the fault of the driver of the motor vehicle. Around 84%, if you see the total number of data. Accidents killed 80% and injured around 83%. So this is what we thought we got a data for. Again, this is data from road accidents in 2016. Again, data has not changed a lot from 2016 till 2024, is more or less consistent. And this is what can be avoided if appropriate warning is provided to the driver of the vehicle. It's obvious. So this is a reason to be worried of. So this is something that is a human. Typically, human involvement is there for 80% of the road accidents. You got beyond 80% of the road accidents. As this is again the same data what we have got here as well, fault of the driver. around 80%. So this is what I believe can be avoided if appropriate warning is provided to the driver of the vehicle. The most accidents happen because if somebody dozes off, if not appropriate warning is given to the driver, obviously accidents will happen. There should be some sort of alerts or some sort of sensory information that should be communicated to the driver so that he can act on a specific time, so that accidents can be avoided or at least can be minimized. So V2V, vehicle to vehicle, vehicle to infrastructure, and infrastructure to vehicle communications can address up to 81% of the traffic accidents. This is something that has been shown to alleviate the problem of the traffic accidents. Whether two vehicles are trying to communicate with each other, or vehicle is communicating with the infrastructure, or infrastructure is communicating with the vehicle. So this can address up to 81% of the traffic accidents. So there are different nomenclatures for V2X. So X in this case can be anything. Just like in maths, you have X that is unknown, but in X in this case can be substituted with anything as far as entity is concerned. So vehicular to X, X can be infrastructure when the vehicle is trying to communicate with the roadside infrastructure as a lamp post or anything else. So this is what is known as a vehicle to infrastructure. There can be vehicle to network. The vehicle is directly trying to communicate with the network to upload the data, to upload the data, and any other applications as well. Then another X can be another vehicle. So vehicle to vehicle. This vehicle is trying to communicate with another vehicle and exchange of some sort of information. Or vehicle to pedestrian. So obviously this vehicle is trying to communicate with the pedestrian for exchange of information. If somebody is jaywalking or something like that, some alerts can be given to the vehicle to stop the car on time or something like that. So again, there are different modes of X. I've already suggested 4, but it can go beyond 4 as well. It can be cloud, it can be server and other entities as well. But these two are prominent, vehicle to infrastructure and vehicle to vehicle. And most of the vehicular communication research has been typically focused on these two areas, vehicle to infrastructure and vehicle to vehicle. Okay. So vehicle to everything, as I've already mentioned. So it can be, it can have potentials of application. Vehicle is trying to communicate with the pedestrian. This vehicle also trying to communicate with the pedestrian. This can be emergency vehicle that's trying to communicate that information to nearby vehicles. Then vehicle to pedestrian, VLC based V2X communication. This is also what we're going to discuss in today's lecture, how a visible light communication can assist in vehicular communication. Then another application can be intelligent platooning, where you can see vehicles are basically, there's a lead vehicle and this lead vehicle is trying to guide the remaining vehicle. This is a very important use case in US. Where there's a lead vehicle, which is specifically in highways, that is leading all the remaining vehicles. This is again a very, very potential application for vehicular to vehicular communication. Then there can be real-time mapping, UAV assisted V2X communication, blockchain assisted V2X. So there are a lot of things that can be explored as far as V2X communication is concerned. Okay. So vehicular applications typically can be quantified into two parts: safety applications. These are primarily, as I've already mentioned, based on V2V and V2I. When the two vehicles are trying to communicate with each other, or a single vehicle is trying to communicate with multiple vehicles, that we typically quantify as V2V communication. And V2I is basically vehicular to infrastructure, or it can be infrastructure to vehicle, I2V. So this is a sort of, again, this two comes under the purview of safety application. The non-safety application can be giving information on mobility, environment, infotainment, and all these things. And typically in this lecture, I'm not going to focus on the non-safety application. I will just focus on the safety applications of how can we use V2V and V2I for safety applications or for vehicular communication. So whenever we want to talk about safety, we need to understand the requirements as far as communication is concerned. So am I right? So because safety is something that is dependent on at what time your information you want and what type of information you want and how periodically this information you want. And the problem with the vehicular communications, a lot of things that happens is since the vehicle is an entity that is always, or mostly it's mobile, am I right? And mobile, because of the mobility, the latency requirements may vary depending upon at what speed you're going, at what distance you're covering, and all these things. So the latency requirement and minimum distance requirement or maximum range requirement typically varies, and what sort of warning you want. So latency requirement, in the sense of it. So the important use case in this case is that if you want to give appropriate warning to a driver, the warning should be given at appropriate time, at appropriate distance. If the information comes at very late, obviously the accident would have already been happened, or collision would have already been happened. or information comes very early, then again it's of no use. The channel would have changed, or the vehicle in front of it would have changed. So this information is again of no use. So you need information at appropriate time and at appropriate distance, so that action can be taken based on this appropriate time and appropriate distance. So this is some sort of data what we have collected. Again, data is very, very important in order to make some inference, in order to make some decisions based on this data. Specifically for V2V, what we have observed was that latency requirement typically varies from 20 milliseconds to 0.5 seconds. That can give you post-crash, pre-crash warnings. So suppose a crash has already happened and the vehicle in back of it, the crash, the following vehicle want to get some warning. So this is a typical range or latency requirement in terms of 20 milliseconds to 0.5 seconds. If it isn't received within this time range, obviously it's of no use. Similar distance range is around 50 meters to 300 meters. Similarly, if you want to provide a warning to a driver on blind spot or merge warning, it should be around latency requirement is around 100 milliseconds. So range is 150 meters. Do not pass warning, lane change warning, emergency electronic brake lights, assistance, and all these things have different latency requirement and different distance requirement. You got it? Similarly, when I talk about V2I and I2V, vehicular to infrastructure and infrastructure to vehicular, again, there is some sort of latency requirement and there is some sort of distance requirement that should be followed in order to avoid collisions or accidents. So reduced speed or work zone warning, it should be given in 1 second, or distance should be 300 meters. Pedestrian and signalized cross, something like a jaywalking, so 100 milliseconds and 200 meters. Curb speed warning, 1 second, 200 meters. Stop sign violation warning, and all these things are different latency requirements and distance requirements in most of the cases. The problem what we see is that these requirements are very stringent. So whether the existing standards, when I talk about DSRC, dedicated short range communication, that is 802.11p from IEEE, or if I talk about cellular V2X from LTE or NR-V2X from 5G, whether these standards are able to meet these requirements or not. This is a very stringent requirement that should be followed in order to avoid the accident cases or collision cases for that matter. Okay. So if we talk about current V2V communication technologies, suppose this vehicle wants to communicate with any of the vehicle, what are the existing technologies that will facilitate a communication between this vehicle or any other vehicle? So we did some, again, research on this part of it. So we came to know that DSRC is the most prominent one. DSRC is basically dedicated short range communication. It's based on IEEE 802.11p standard. It's also known as WAVE standard, wireless access for vehicular environment. And this is the oldest standard for vehicular communication. It's most dominant one as well. And whatever cars are available, typically some of them are following this 802.11p standard for vehicular communication. In addition to this, there are cellular standards available as well. Cellular, as I already mentioned, LTE V2X, that is based on 4G, or NR V2X, that is based on 5G, also exists for vehicular to communicate with each other. Then there is a conventional Wi-Fi that is also can be used to communicate between the two vehicles. Currently, the Wi-Fi is predominantly used for infotainment system. So if you drive a car, latest car, typically you have a Wi-Fi based infotainment system where the Wi-Fi is being used to communicate between your mobile phone and the car stereo and any intelligent device that is incorporated in your car. So this typically they use Wi-Fi direct or Bluetooth to communicate for infotainment, but the same Wi-Fi can also be used to communicate between the two vehicles as well. In addition, there can be millimeter wave and other techniques as well. One of them is visible light communication, where you can use car headlights and tail lights as a means of communication between the two vehicles. Then there can be, as I mentioned, millimeter wave is also very prominent technology that can also be used to communicate between the different vehicles. And we may never know in 2030 what sort of technologies may pop in to communicate between the two vehicles. So this is something that is existing literature, and then we need to find out what are the drawbacks of these techniques and how can we propose a new technique that can alleviate the drawbacks of the existing techniques. You got it? So whatever we have done till now, if you see in terms of work that has already been discussed from me, we have found out the use case first of all. Then we found out what are the problems with the use case, and what are the basically requirements, and then what are the existing techniques that are proposed to alleviate these problems. The existing techniques are these three techniques: DSRC, cellular, Wi-Fi. Going forward, we can see how these existing techniques perform, and can we do something? Can we do some research, or can we propose a new techniques that is better than existing techniques and can also meet the requirement of latency and the range to solve some of the problems related to the vehicular communication? Okay. So as I already mentioned, current V2X technologies are typically based on vehicular Wi-Fi. As I already mentioned, this is 802.11p standard. It was proposed in way back around 14 to 15 years back. It's fully distributed random access. Whatever properties you have of Wi-Fi, it also there in vehicular Wi-Fi. And recently 802.11b as a improvement on 802.11b was proposed by IEEE in 2022. Similarly, in cellular context, there are prominent technologies that's LTE V2X that is based on cellular infrastructure for extended to vehicular communication. So infrastructure downlink and uplink, and for direct V2V, it's typically proposed device-to-device communication. It has a time frequency structure. And again, recently in 2020, it was proposed 5G V2X, that's vehicular communication based on 5G standard. And there's recently upgradation done in 2022, release 17, that also incorporates some of the features for the vehicular standard. So these are a current state of the art. And let's see what are the issues with this sort of standards. So again, I will not go into details of it. There are a lot of literature that is already available that shows the problem about its existing standards for vehicular communication. The prominent among them is channel congestion, mutual interference, delays, and packet delivery. And because of that, some of the stringent requirement, whatever we saw in terms of latency and distance, may not be met by these existing standards. If I talk about 802.11p, or if I talk about cellular V2X, or in fact even NR V2X. So this has its own baggage of problems. Because of that, they may not be able to meet the stringent requirements of the latency and the data range, latency and the range that is required to avoid collisions or accidents. Again, same drawbacks. 802.11b, so this is CSMA CA based collision, multiple access collision avoidance, and so this is a latency requirement is 20 millisecond that may not be met. So DSRC, that is current standard, is affected mainly by high traffic densities, non-line of sight requirements, and high velocities. This factor reduces the communication range, causes numerous packet collisions, increases the delays, and reduces the reliability. Clearly, 802.11p standard does not met most of the requirements of latency and the range. Same if I talk about cellular V2X. Cellular V2X typically have two different ways to realize vehicular communication. One is the vehicular to network V2N, where you have dedicated spectrum where the vehicular can communicate with the network, or network can communicate with the roadside units, and pedestrian can communicate with the network. So this is something that is based on licensed cellular spectrum. However, the vehicular wants to communicate with each other, like vehicle wants to communicate with the roadside units, or vehicle wants to communicate with the vehicular, or vehicle wants to communicate with the pedestrian. They typically use PC5 link, that is what we call as side link, and that facilitates device-to-device communication. That is based on 5.9 gigahertz intelligent transportation system band. So for cellular, they use both type of spectrum, licensed and unlicensed. This is the problem in the cellular. The main challenge for cellular V2X is to have a dedicated spectrum needed for vehicular to network communication. And that may or may not be available most of the time, because spectrum, anyways, we know is a very, very expensive resource. And apart from that, the Doppler involved with vehicular communication and frequency shift at high speed, the current, at least cellular infrastructure may not be able to support such high Doppler spread, and obviously high density scenarios when you have mobile users, when you have vehicles and other entities as well. The performance of cellular networks typically goes down tremendously. So now we got an idea that, okay, these are existing solutions that are available for vehicular communication, and what are the bottlenecks or problems with the existing solutions. So can we come up with a new technique that is able to solve not all, at least maybe some of the problems of the existing techniques, and maybe help to facilitate the latency and the distance requirement for the vehicular communication. So doing some research, we were already have a lot of expertise on the visible light communication. So we thought, why can't we use VLC as a means for vehicular communication? So that's why we started working towards it. And I think some of you already know the ranges of optical wireless communication. So optical wireless communication typically consists of 3 different bands: infrared, visible, and ultraviolet. Most of prominent communication systems for OWCs typically exist on infrared and visible. Infrared has been there for ages. If you remember, your TV remote control on all this were typically based on infrared communication. Nowadays, you can use your Wi-Fi also to control the TV, but previously all the remote, even most of the remote controls till date is based on infrared sort of a communication system. And obviously, visible light is something that you have been using for some time now. You use visible light to see, and the same visible light can be used as a means of communication as well. The beauty of visible light is that it's a huge chunk of band available from 430 terahertz to 770 terahertz. That means huge amount of spectrum is available. And obviously visible light can never be licensed by any of the entity because you cannot license the LED light, right? You cannot say that you cannot install LED at your home and you need to pay for some sort of license. That I think, as far as I know, it's sort of pretty impossible to license it. So this is something that is a benefit of visible light communication. Advantages of VLC integrated with the lighting system. Obviously, whatever you see when you talk about LEDs in your home, offices, or in fact in vehicles also can be used as a means of communication. And another benefit of VLC is that technologies are complementary in nature and will coexist. So the VLC band or the visible light communication band is completely different from the conventional radio band. And obviously these two will never interfere with each other. So these two can coexist without interfering with each other. So it's best of both the world. You can also use RF. You can also use visible light as a means of communication. So there's a lot of misconception that goes about the terminology. So VLC is typically visible light communication that is typically restricted for downlink communication from LED or light emitting diode or laser diode to the photodetector by using visible light. Okay, so when the LED is trying to communicate with the photodetector, we typically use visible light as a means of communication. When I talk about Li-Fi, Li-Fi is typically coined as a term that was coined by Professor Harold Haas a few years back. That also consists uplink. So downlink is visible light, obviously from LED to the photodetector. But uplink can be infrared, visible light, or ultraviolet. Typically, infrared is more prominently used, but it can support any of the three technologies. So you have bidirectional communication in Li-Fi. Another one is optical camera communication. So there's lots and lots of research is currently going on in optical camera communication. How can you use your camera as a means of communication device? And in fact, we have also have a test bed on this one also, where we have shown that camera can also be act as a potential receiver. Again, this is through visible light and infrared. And then obviously you have free space optics link that uses laser diode and photodetector. And typically it can be based on infrared, visible light, and ultraviolet. For this lecture, I'll just focus on VLC aspects of it, and I'm going to assume that your vehicles are embedded with an assumption that's not incorrect, because nowadays if you buy any vehicle, typically it will have light emitting diodes as a means to illuminate the roads and all these things. Okay, so the same lighting properties whatever your vehicle has can be used as a means of communication as well. So visible light based vehicular communication, again I don't need to go into details of it. So obviously all the cars, all the vehicles, we're talking about two-wheeler, even e-rickshaws nowadays, or cars, trucks, most of these cars typically have embedded LEDs into it. And the same LEDs can be used as a means of communication. And the beauty of LEDs is the high directivity, short range, and the requirement of line of sight communication. There's some bottlenecks as well. There's no free lunch. So obviously there's some problems with the LED lighting as well. It's sensitive to weather conditions. So you might have heard that visibility has dropped to 50 meters, visibility has dropped to 0 meter in Delhi. So whatever you're able to see is whatever you're able to transmit. So obviously, if you're not able to see beyond a point, you will not be able to transmit beyond a point using visible light. So visible light is very, very sensitive to weather conditions, whether it's fog, whether it's rain, whether it's smog, whatever it is very, very sensitive to weather conditions. The challenge in this case becomes how to make it robust to the noise, other sources of the other lighting sources in presence of sun, lamps, or in presence of other weather conditions, and how to enhance performance in mobility. So this is a work that we have been doing for some years now, and I will just present some results. I will not go into details of the mathematical, in interest of time, not into details of mathematical equations, derivations. Sometimes that loses interest of the audience. I will just try to give a big picture and how we use the visible light as a means of communication for vehicular communication, to be more specific. So we did a lot of studies, outdoor scenarios with respect to vehicular VLC. We first studied the impact of solar irradiance and fog conditions on the performance of vehicular VLC. Then we studied the impact of interference from single interferer. Then we studied the impact of interference from the multiple interferers. So we went step by step. First was the impact of the weather conditions of the performance of vehicular VLC, then the impact of interference, and then the impact of multiple interference on the performance of vehicular VLC communication system. So first was the impact of solar irradiance. Obviously, you cannot avoid the sun. Obviously, being in Delhi in the summer months, you cannot avoid the sun. So sun will obviously have an impact on the vehicular communication. It's same everywhere in India, whether you talk about Jaipur or Mumbai or Chennai sun is always going to be present. So because of the sun, there is always going to be interference or noise level when you're trying to communicate between two cars using vehicle headlights and tail lights. So we did studies for two different cities. One was New Delhi and one was London. So obviously sun has its own impact. But the thing what we observed was depending upon the month, the solar radiance varies. So in which month you're doing the transmission, according to that, your performance may vary. So this is a BR evaluation what we did for 3 different months for New Delhi, and again there's 3 different months for London as well. Obviously, performance in London is slightly better than New Delhi because the impact of solar irradiance in London is slightly less as compared to New Delhi, because New Delhi receives more sunshine hours as compared to London. So obviously the impact is less. But later on, we also, I will not go into details of it. If you want, you can refer to this paper. We also showed some techniques through which, by using appropriate filters, you can further improve the performance in sunny months as well. We talk about March and June. You can again improve the performance by using appropriate filters that can filter out the DC signal due to the sunlight. Then we studied the impact of fog conditions. Obviously, fog is one of the major bottlenecks as far as vehicular communication is concerned. As I already mentioned, during the foggy conditions or during the smoggy conditions, the distance typically, the range of the vehicular communication using visible light typically reduces. So what we observed was that, again, we quantified the fog in terms of what we call as a visibility parameter. And again, I will not go into mathematical interpretations. So this is attenuation that results or the impact of the visibility because of the attenuation factor. Okay, so depending upon your wavelength at which you are transmitting, attenuation coefficient typically varies, and depending upon at what distance you are trying to transmit, again your attenuation values will change. So this is what we quantify in terms of depending. So if you are having dense fog, your attenuation dB per kilometer will be 78.8 dB. If it's light fog, it's 79.4 dB. If it's rain, 21.9. If it's wet snow, 19.86. If it's dry snow, is 131 dB. So depending upon the weather conditions, your attenuation parameters will be changing. So what we thought was that why not we get some pattern from a car headlight and see how these weather conditions typically impact this pattern. So this is a pattern for original equipment manufacturer for Toyota Corolla Altis car. And this, you see, this is a sort of a tweak. It's not like a very symmetric sort of a pattern. This is a misconception that car headlights are a very symmetric pattern. So they're tweaked a bit to the right hand side so that the headlight typically falls on the road. It's not very symmetric. That's why the power levels, if you see, are different at different distances. So if I take, suppose this car headlight is here, and if a distance is 100 meters, the received optical power is not uniform per se. You got it? So this is something that we observe for this sort of car. That is, the pattern is not very unique. And this is unfiltered pattern. This does not contain any impact of this weather condition. This is without any impact of any weather conditions. So on the top of this pattern, we superimpose the impact of different weather conditions. Again, I will not go into details of the analytical derivations and all these things. I will directly show you the results. So you see, in absence of any weather impact, the level you're getting is minus 55 dBm at 100 meter at this point. So if the vehicle is located here, the receiver vehicle is located here, and the transmitter vehicle is here, the receiver power will be around minus 55 dBm in absence of any weather conditions. But in presence of any weather conditions like dense fog, the receipt power reduces to minus 63. In light fog, it reduces to minus 59, and in rain, it reduces to minus 57. So this is what we observe in presence of different weather phenomena, the impact at the receiver side of it. And we extended it to dry snow and wet snow. Again, you can see the visible change in the weather, visible change in the pattern in presence of different weather phenomena. So this is the first study what we did. Then what we did, as I've already mentioned, we studied the impact of interference sources as well. So obviously you are not the only guy in the road that will be transmitting using car headlights and tail lights. There would be other cars, there would be lampposts and all these things that would also be transmitting using car headlights and tail lights, obviously. So we started with the first level of interference. So that this vehicle, car B, is trying to communicate with vehicle A. And there's a car C on the side lane, and that is also trying to communicate with other vehicles. But obviously the car headlight of this one is going to interfere with this one. So how can we alleviate this interference? This is what we studied as a first part of the work. Again, skipping the analytical details, this is what we observe. So in presence of interference, as well as depending upon the distance between the interferer vehicle and the desired vehicle, the communication range typically reduces. Just to summarize this result is that suppose your communication distance was 100 meters, in absence of any interference or in absence of any fog or weather impact, it reduces to 45 meters depending on whether it was dense fog, light fog, and depending upon what is the vehicular distance or interference distance. This is one of the studies what we did and find out not only the interference, the weather also has a significant impact, and not only the weather, the interference also has a significant impact on the performance of a vehicular visible light communication system. Then we extended to multiple interferers. There are multiple interferers on the adjacent road, so there are multiple vehicles, and we then took help of stochastic random process to, in fact, model the number of vehicles on the road which are acting as an interference to the desired vehicle. Again, so there are a lot of mathematical derivations were involved in this case. I'm skipping some of them. So these are the results what we obtained, and we define in terms of probability of successful transmission for 3 different traffic scenarios: sparse traffic, medium traffic, and dense traffic. So these were results what we obtained for 3 different traffic scenarios. Just to summarize the results what we obtained was that, so this interesting observation what we got was that, so we compared with the conventional DSRC, that is a VRF we are going to call it, the dedicated short range communication, IEEE 802.11p, that is typically used for, is a slightly conventional standard that is typically used for vehicular communication, and we compared the performance of the visible light communication based vehicular communication with respect to RF communication. And what we observed was that in normal atmospheric conditions, if everything is rosy, there is no fog, there is no rain, there is no snow, nothing is there, so VLC is good, no doubt about it. It doesn't matter whether it's dense, medium, or sparse, VLC is always going to be good. VRF, on the other hand, if it's a dense traffic, then obviously it doesn't work. There are a lot of vehicles flying on the road, and there's a contention issues. Every vehicle is trying to get access to the network. The same problems you have with the Wi-Fi. When there are large number of users trying to access the same access point, throughput per user will start to decrease. The same problem is happening in the vehicular communication. But in medium traffic and sparse traffic scenarios still works, but in dense traffic scenario doesn't work. Another interesting observation what we got was a VLC. Even if there's a light fog, it doesn't work in medium and dense. So VLC is a very, very significant impact. The weather is a very, very significant impact on vehicular visible light communication system. And same thing we observed for dense fog and dry snow conditions as well. So now what to do? So for some cases we observed VLC is good. For some cases we observed RF is good. Why don't we marry these two? So this is something that we proposed. So this is first just some set of results with interference and light fog and dense fog and all these things. Again, this is a pattern what we observed in terms of different impact of weather conditions and different impact of interference. So again, coming back to, so these two are good in terms of silos. Somewhere VLC is good, somewhere RF is good. Obviously, these two are complementary. Why don't we combine these two? This is what we call it as a hybrid to start with. Then we're going to jump into link aggregation. So you see, VRF is good when power consumption is, so VRF is good when you have non-line of sight cases and when you are not sensitive to electromagnetic radiations and all these things. And VLC is good when the impact of ambient light is less or weather impact is less. And you see, these two are very complementary. Red and green have very complementary nature. So what we thought of is, why don't we combine these two? The obvious question is, why don't we combine these two? Because somewhere RF is good, in weather conditions RF is good, in clear sky VLC is good. Let's combine these two. So this is what we proposed as a hybrid VVLC VRF system. Next work. So use case hybrid RF VLC VE2I communication system. So what we are proposing in this case is that suppose this yellow vehicle is trying to communicate with this blue vehicle. I hope I'm still there. I didn't lose the connection. Everybody's just to interrupt. Hello. I hope I'm still audible.
Yes, sir.
Okay. Thank you. Yeah. So just coming back to the same figure. So suppose there's a yellow vehicle, a yellow car on the road that is not able to see the blue car, but it wants to communicate with the blue car for whatever reasons. So so maybe there's another vehicle and the light is not working. So this may also cross it. This may also cross it. There's a high probability of accidents, specifically at road intersections. So we took 2 different cases specifically at road intersection because as far as Delhi is concerned or any other city is concerned, road accidents are high collision zones. You got it? Because if the signals are not working, specifically late in the night or early in the morning, there's high probability of collisions because there would be some vehicles coming from here, some from here, and the collision probability is very, very high. And so use case for us was, suppose this vehicle wants to communicate with this vehicle, and since it's not able to see to each other, how can we use a hybrid RF VLC to ensure this communication takes place? Okay, so this is a use case that we're trying to solve. Again, traffic intensity and basic safety messages and coordinated so obstruction is there, and obviously there are a lot of packet collisions may pop in because a lot of other vehicles flying on the road. So this is a system model, and it was published in Intelligent Transportation Systems. So again, this is a roadside units are there here, and this is a vehicle that's trying to communicate with the roadside unit by using a lamppost as a VLC and also as a means of RF as well. And there's other vehicles D1, D2, D3. They're acting as interfering vehicles to this desired vehicle. And since it's a hybrid architecture, so state diagram comes into picture. So there can be three different links. Either it's a VLC link or is a RF link, or obviously if both of them doesn't work, it's outage. Outage in the sense of it, power outage is a very, very common term. So if both the conditions are not satisfied, it will go in a outage. So what basically this state diagram basically means, it will first try with a VLC link. If it works, it will stick to the VLC link. Then it will move to the RF link. If this doesn't work, it will move to the RF link. Check with the RF link works. If it works, it will continue with the RF link. If both of them doesn't work, obviously outage will be declared. That means both the links are not possible and this communication is not possible. So again, we did a lot of work in this area, and we found out that obviously hybrid, the green curve in terms of outage is performing better than standalone VVLC and standalone RF cases. This is an interesting observation what we obtained. For vehicular communication, where we use a hybrid that get best of both the worlds, obviously going to perform better than a standalone VLC or standalone VRF. Again, we tried for different ranges and different scenarios. Obviously, hybrid is always going to perform. We are giving it 3 stars as compared to VRF or VVLC cases. This is the first work what we did as far as hybrid technology is concerned. We also did a lot of other works as well, but I'm not going to go into details of that other works. But this is something that we did as a VVLC, VRF cases. Then what we thought of that, so why not we do something for the problem what we see is vehicular communication is a non-line of sight. Typically in a road intersection, if you remember the pictorial what I showed, something like this. So suppose this vehicle wants to communicate with this vehicle, this is not able to see each other. Either it has to use some sort of a relay or some sort of a mechanism to extend this communication to this vehicle. So we thought of why don't we use something what we call as a RIS. I think anybody who's currently working in wireless will know what is RIS. RIS is typically reconfigured intelligent surfaces. A lot of people call it as IRS, intelligent reflective surfaces, programmable meta surfaces, software controlled meta surfaces, software defined meta surfaces. A lot of names have been popped up, but basic definition is that it's reconfigurable. That means you can reconfigure the elements, you can modify the phase and amplitude of the elements. It's intelligent. Intelligence in the sense of it can sense the environment, and accordingly by sensing it can take a decision. And obviously surface, it's a planar surface. It can be installed in a facade of the building, on a vehicle, on the road, anywhere you can think of it can be installed. And it's nearly passive in the sense of it doesn't have a lot of active components, and it doesn't consume a lot of power. So these are some of the properties of RIS. So same thing what we thought, can we use RIS to alleviate this problem of non-line of sight for vehicular communication? So again, this is some of the properties of RIS. So transmitter wants to communicate with the receiver. There's non-line of sight. It can take help of RIS to communicate with the receiver. And this is a setup what we have in IIIT Delhi. And we demonstrated this RIS setup in multiple avenues as well, where we practically demonstrated the use cases of RIS for different antenna configurations. And we tested it on a LTE stack, the 4G stack, and we showed that RIS in fact can improve your communication performance if there is non-line of sight condition between the transmitter and the receiver. So this hardware deployment what we have in the IIIT Delhi. So same use case, that this car, the yellow car wants to communicate with the blue car, and obviously there is no way it can do it because these two cars are not able to see each other, and there's high probability of collision between these two cars. Suppose signals are not working late in the night, drunk driver, whatever cases may be. So can it take a help of RIS to communicate with this vehicle? And this work, again, I will skip some of the analytical derivations, and this was published in IEEE Transitions in Vehicular Technology. And so this was the study. And so this is the system or this vehicle wants to communicate with this vehicle, and it can take assistance of RIS to do so. The first link is from vehicle to the RIS, second link is from RIS to the destination vehicle. Okay. and we compared it with a relay technology. So obviously we need to benchmark for comparison, and we didn't compare with any relay. We assume that the first link is VLC and second link is RF. So we try to make it a little bit complicated. It's not like a conventional RF relays. We assume that it combined, it's a hybrid, what we already know, VLC plus RF. So this is what we try to compare with, so that we cover all the use cases. So we are comparing with RIS with the relay system. Okay, relay basically consists of VLC plus RF. Okay, again, without going into nitty-gritty of the analytical derivations and the simulation scenarios, so this is something that we obtained. Again, if you want to go into more details of it, obviously you can refer to this paper. So what we observed was that so blindly deploying RIS may not help. You got it. So this is something that is an interesting observation in our case, and it also depends upon how many mirror elements or how many elements you are typically allocating for this RIS. You got it. So depending upon what sort of criteria you are following for spectrum access probability, and depending upon the distances, for some cases relay will be better. For some cases RIS would be better. That's an interesting observation. With all the hype around RIS, so that's not always true that RIS may always help. There are some specific scenarios at which RIS can help. There are some specific scenarios in which case going with the conventional relay systems makes more sense. So this is what we observed. This is the first observation what we did. There's always a case by deploying more number of mirror elements, not taking into account additional cost, deployment cost, and all of the features. But there's always going to be a case where if you deploy more number of elements, the performance will be slightly better. Then there's always going to be a cutoff in terms of number of elements you can install that will help you to perform better than the relay cases. That is also something that we observe. So there are two observations in this study, just to summarize. First was that RIS may not always help. There would be some cases where relay will be perform better than RIS. However, there can always be a case by increasing the number of elements, you can have a performance that is better than the RF or better than the relay cases. This is something that we observed, and we evaluated for different delay outage rate, information outage rate, and all these different parameters in terms of throughput, latency, and all these things. So these are something that we observed for this work. Okay. Then what we thought was that, so this was purely on the RF RIS. Then we thought of why don't we extend it to something what we call as optical RIS. Again, we did a lot of work on the optical space of RIS. So what we thought of that, what happens if I install RIS on the road surface itself? You have a lot of reflectors on the road surface. If you drive, there will be a lot of reflectors, speed breakers, and can some of the speed breakers will be replaced by what we call as optical RIS. Again, the same use case, road intersection. This vehicle wants to communicate with this vehicle, and there's a building, and obviously this is not able to do so. This is demonstrated using red line. So this vehicle will take a help of what we call as optical IRS to communicate with this vehicle. Obviously, that makes sense. Am I right? So instead of deploying on the buildings, facade, and taking lots of permission, replace a speed breaker with not replace a speed breaker, modify the speed breaker to consist of IRS, or modify the reflectors or radium reflectors with some sort of RIS devices. Why not? So this is what we did. We studied this phenomena, and this we modeled as an intelligent mirror relay. So a lot of people don't know what is a mirror array, first of all. So intelligent mirror array in the sense of it. So if you drive a car, what you typically do is, if you want to see in the back, you typically adjust the mirror. Nowadays, you can do it automatically. Previously, you need to take your hand out and put the mirror such a way that you can see in the back. Ultimately, what you're trying to do is that you're adjusting the mirror location so that the reflection that you're getting from the back is getting from your eye. You understand? So you're able to see through the mirror what is happening, there's a vehicle in the behind or something like that. Same concept we have incorporated in this case. Now, instead of doing it manually, is intelligence. So in this case, what we're trying to do is, suppose this vehicle wants to communicate with this vehicle. So we can orient this mirror or number of mirrors so that whatever light is falling in this mirror is going to be reflected to this car. Understand what I mean to say? So there's a car that is trying to communicate with this car, and this mirrors will help you to do so. So this mirror will orient itself such a way that whatever light is falling from this car to this car will be reflected to this car. So this car is now aware there's another car approaching, so the collision can be avoided. So this is something that we proposed. This was a very, very interesting idea. And this also won the best paper award in IEEE AND 2022. Again, without going into nitty-gritty of the maths, because without maths, sometimes it's very difficult to prove what we intend to do. So this is something that was a broad idea, and we showed that actually it works. So this vehicle can communicate with this vehicle, given some distance, given some following the Snell's laws and all these things, and given the orientation of the mirror, this vehicle will be able to communicate with this vehicle at an appropriate distance, at appropriate range. So this was something that we did with optical IRIS and all these things. And apart from that, we also did a lot of work on the allocation of the resources to the vehicles. Again, these are all published work. I will not go into details of it. How can we allocate optimal resources from roadside units to different vehicles, whether in terms of wavelength, and obviously we applied a lot of machine learning algorithms for these type of cases. And we showed that what are different use cases for V2I. So these are typically for V2I, I2V, what are delay, reliability, throughput, and what sort of requirements are required for different use cases, extended sensor, advanced driving, and remote driving. And based on this one, we allocate a lot of resources. And all these are published in vehicular communication transactions, how we are doing optimal resource allocation from the roadside units to different vehicles. And another interesting thing what we did that got was actually worth talking about is that we got some sort of data. Again, data is very, very important, as already mentioned. The number of vehicles plying on the road and how many vehicles will actually need resources from the RSUs. Okay, we still have time. So then we did some sort of vehicle prediction, and we used 3 different models: linear regression, random forest, and cat boost model. We found that random forest is performing is a very good trade-off. Linear regression was not very good. Cat boost model was slightly complex, so we stick to random forest, which was sort of ensemble of all the readings whatever we obtained. And using this random forest model, we did some sort of vehicular prediction, and based on this vehicular prediction, we allocated a lot of resources on the vehicle. So this is again was published in Vehicular Communication, and this is something that we currently are doing. And then apart from that, these are 2 transactions we recently obtained, and this is again a different sort of a work. In this case, what we're trying to do is that just to give a hint of it. So basically, the number of vehicles plying on the road sometimes is very, very difficult to make the decision on a fly. Am I right? Because there's so many vehicles, so many entities flying on the road, and suppose there's a vehicle here which suddenly applied brakes. So obviously there's a high probability this vehicle will collide with this vehicle. Sometimes these sort of decisions cannot be taken on a fly. So what we did was that we used what we called as a concept of metaverse, or basically digital twin. We replicated a complete scenario on a cloud, and then we made some inferences on the cloud, and based on that inferences, we did some real-time modifications. You got it? And this is the complete study has been published in 2 transactions. One is emergency path planning for safe driving in transverse embedded connected vehicle networks. It has actively transition on system man cybernetics. And second is that digital twin for connected vehicle network, a road tool system accepted in IEEE Transitions magazine. So these 2 is a very interesting thing what we did. We emulated the complete traffic scenario on a cloud. Then we proposed novel algorithms so that the inference whatever we are obtaining from the cloud can be applied on the real-time scenarios. So this is something that we did as a part of our work. Okay. Then one more thing what we are currently pursuing is that, so if you see vehicular communication infrastructure, so that is not very easy to work on, because vehicles are always moving, the roads are not very consistent, you cannot have a very straight highway, am I right? So the roads are always curvy in the nature, specifically in hilly areas. Your roads are always going to tend to move from one place to another. In the sense of it, there's always going to be some sort of curves that you are not aware of, and there is high probability of accidents. So we already dealt with the road intersection scenario. We try to deal with the curvy nature of the roads, specifically in hilly areas or something like that. For that purpose, what we thought of that, what happens if suppose we replace a photo detector with a solar panel? So that was sort of a revolutionary idea. In the sense of it, solar panels are typically used for energy harvesting, and very few people have actually used solar panels as a means of communication. But logically speaking, if you see, solar panels are nothing but a photovoltaic cells, or typically like a photo detector. So there is a lot of switching that goes on in the solar panels. The same photovoltaic cells can be used as a means of communication as well. This is what we showed, and we're currently pursuing as well. So what we showed was that this is a complete setup. This is a transmitter unit, there's a receiver unit, and receiver, if you see, this is a very small solar panel that we have used like this. This is a solar panel, as you can see, solar module, and this also we also designed a bandwidth enhancement circuit that is patented from our side of it, and we used a LED as a means of communication with a solar panel. And one of the major use case of something like this is for vehicular applications. Specifically, suppose there's a vehicle wants to communicate with this vehicle, And obviously, photo detector is a very, very small device. Am I right? So if you go out of the range, non-line of sight, you will not be able to communicate with this vehicle. But solar panels typically have a larger area, effective area. So if you replace a photo detector with a solar panel, so your communication range will also increase. And obviously, specifically in areas, roads which are very curvy in the nature, you still be able to, these two vehicles will still be able to communicate with each other. So that is something that we are currently working on, and we are showing that how can we deploy or we embed a vehicle with a solar panel, and this solar panel can be used as a means of communication with the other vehicles. This is the current state of the art that we are currently pursuing. So this is something, as I've already mentioned. So it is a curvy road, and if I install a photo detector, that will typically have non-line of sight. But if I install a solar panel, you will still can be able to communicate between the two vehicles. So this is something that we are currently pursuing. And this is applicable in dead zone areas, the areas where non-line of sight are very, very prominent, and the conventional photo detector may not work because of non-availability of line of sight communications. So in addition to other works, what we are currently pursuing is, as I already mentioned, digital twin enabled connected vehicle network. This is currently what we are pursuing. Optical underwater communication. We have done a lot of work in optical underwater communication as well. Where AUV, autonomous underwater vehicle, can communicate with a diver by using optical IRS. We recently have a patent also in this case, and also some publication where we have shown that optical IRS can be used as a means of facilitating underwater communication. Then obviously Li-Fi is our core research area. We have done lots and lots of work on Li-Fi, CSI sharing, Li-Fi access points. We have designed our own hardware based on Li-Fi, and we have shown how can we coexist with Wi-Fi and improve the performance. And recently, we have also started working on integrated sensing and communication for vehicular applications, where RIS will be used for sensing and LEDs will be used as a means of communication. So this is again ongoing work from our group, in addition to vehicular work that I've already shown. Okay. So just to conclude, so we have shown the potential benefit of deploying VVLC VRF over standalone VVLC VRF network configuration for outdoor as well as indoor scenarios. And we showed different ways these two technologies can coexist and help each other. We also showed how can we use RIS as a means of communication. And then we also showed how we are utilizing digital twin or metaverse as a means to basically replicate a complete vehicle scenario in the cloud and make some inferences and communicate in a real-time scenario. So with that, I will stop. Now I'm open to take any questions in case you have any.
Dear participants, if there is any query, then please turn on your mic. Otherwise, please keep your mics muted. It's my humble request. All the participants, if there is any query, only then turn on your mic. Otherwise, please keep it muted.
Okay, I am on time. I don't wanted to have more of a discussion, so I have kept 15 minutes.
Sir, I think if you are comfortable, then can we take a query that is from Ravi Kumar? And
yes, sure,
we
sure.
do
Go
have
ahead.
the query in the chat box.
So
if you want, I can read it for you.
Great, if you can read it, because chat box, got it, sir. Got it. Yeah, you can read it if you want.
Yeah, sure, sir. So there is a query. What aspects to be considered to calculate CSI from RSSI need mathematical perspective, sir? This is the query.
That's a very interesting question. So CSI is just to give a hint of it, CSI is a very, very broad definition. So RSSI will give you something like a received signal strength indicator, right? It's sort of an analog value. What is the power level and what is maybe more of SNR value sort of it. When I talk about CSI is exact channel state information. Am I right? So just to give you an example, suppose you want to send it specifically for integrated communication, sensing and communication, or even for beamforming, you need to know the exact location of the receiver. Am I right? If suppose you want to do a beamform or when you use a RIS to do a beamforming, if you have the RSSI level, you will not be able to. You will just have some crude value of the power level that is being received at the receiver. CSI on the other end is the exact value of the channel, am I right? That is typically estimated using pilots or preambles. So suppose I want to estimate exact channel information from the base station to the receiver, or from the roadside unit to the vehicle, or for that matter from the transmitter to the receiver, and need to send some preambles or pilots so that that can be estimated by the receiver, and through a feedback loop that channel state information can be communicated to the transmitter. So CSI values are something that is very independent of the RSSI. RSSI values will give you typically power levels, SNRs. But on the other hand, CSI values are raw values of the channel that will help you to do sort of things like beamforming, localization, sensing as well. I hope that answers the query.
So I hope you get your answer, Mr. Ravi Kumar. Okay, sir. Next query it is from Dr. Anshika Malsaria. Can we say the V2X is part of ubiquitous or pervasive computing and also comes under smart city concept?
Again, this is a very interesting question. So it's not fair to quantify V2X as in one silos or in one domain. Am I right? So V2X, as I mentioned, it's not only about how the vehicles wants to communicate with each other, or two vehicles wants to communicate with each other, or vehicle wants to communicate with the infrastructure. So that may come under the purview of smart city also. That may also come in under the purview of offloading as well. Suppose just to give an example, there's a lot of data that is generated by the vehicles. Am I right? If you remember, I showed some cases of digital twin and metaverse. So there are lots and lots of data that is being generated by the vehicles. How are you going to ensure that this data is being communicated to the cloud? Am I right? And what sort of computations you will do based on this data, what you have gathered from the actual vehicle scenarios? So if you restrict yourself to the smart city concept where you're just focusing on the safety applications, it's not correct. Am I right? You, apart from safety application, what you also intend to do is how you want to design the optimal route. Am I right? How you want to minimize the power consumption or fuel consumption, how you want to minimize the carbon footprint. So safety is a very, very important aspect. I'm not denying safety is a very, very important aspects towards it. But in addition to that, if you talk about cities like Delhi, which in that case you just like a bumper to bumper traffic, you like sort of waste a lot of fuel. So if I can get some data which is optimal routes, apart from the GPS data I'm talking about, if you can get the data of what is the optimal route and which route if I take result in lower fuel consumption, that itself will help us to alleviate a lot of problems that are there with the vehicular connectivity. So it has an application not only in terms of smart city, but also in terms of ubiquitous computing, or maybe data offloading to the servers, data offloading to the cloud, or plethora of other applications as well. Yep. I hope that answers the question.
So can we take next query?
Yeah, sure. Go ahead.
The next query is from Nagarajan. The query is, what ethical considerations arise when V2X systems prioritize certain vehicles in high-stake scenarios? For an example, ambulances over private cars.
So as a technologist, I think this is not, I may not be the appropriate person to answer this, because ethically, obviously you have to give a way to the ambulances. A lot of cities, I've lived in a lot of cities across the world, they have a dedicated ambulance lane. In India also, now things are changing. Typically you have a dedicated right lane is ambulance lane of government initiative as well. So because as a technologist, I cannot answer that question, because it's more of a what priority you want to give. You got to mention. So suppose you reserve a complete lane for ambulances, then obviously traffic congestion will increase on the other. There will be a lot of pressure on other lanes. But obviously you want to prioritize emergency cases, emergency scenarios. So obviously dedicating a separate lane makes more sense, ethical consideration. But the reverse impact of that one will be that your other traffic scenarios or congestion on the other routes will obviously increase. So technologies, well, I don't know what sort of answers should I give in these questions, but my personal feeling is that there can be an optimal trade-off depending upon what sort of protocol you're trying to follow. The best case scenario is that if there is some sort of emergency vehicle like fire brigade or ambulance, you should give it away and ensure that passes without much hindrance or obstructions. This is the maximum what I can say.
Nicely explained, sir. From the same participant, there is another query, that is Nagarajan, that what measures are necessary to protect vehicular communication networks from cyber attacks like spoofing and data interception?
So I didn't cover the aspects of the security aspects. That is again, frankly speaking, that's not my core research area. But there are a lot of. So if you see about just to give an example of DSR, so DSRC follows the same security protocols, AES protocols which Wi-Fi follows. If you talk about 802.11 BD, I think that has some sort of upgradation in terms of security features as compared to the conventional 802.11p standards. But obviously, it doesn't matter how much secure the system design is. There's always going to be some sort of spoof or eavesdropper that will be trying to listen to the conversation. But there are a lot of other ways to minimize something like that. As I already mentioned, there maybe you can deploy RIS that can alleviate the impact of eavesdropper, or can do some sort of destructive interference at the eavesdropper side of it, or you have necessary checks and balances in place before allowing any user to enter the system. So these are few ways through which you can improve the security of the vehicular communication networks.
Thank you, sir. And from the very first query, there is a comment from Mr. Ravi Kumar. To be more precise, I don't have closed loop from receiver to transmitter. Just I got an ESP32, which is receiving signal from Wi-Fi router. How to get CSI in this case?
That's it. So without the feedback loop, correct. So without the feedback loop, is going to be very, very tricky. Am I right? So without the feedback loop and without the preamble, either what you can do, there are a lot of statistics. The channel is more or less static. Again, this is my food for thought, maybe in your case. If the channel is more or less static, so the CSI will not change over a period of time. Maybe you can measure the CSI for that specific scenario and use the channel estimates and feed the channel estimation to your receiver. Am I right? This is one thing what you can do. Theoretically, measuring the CSI from just RSSI is impossible until unless you know the preamble, or either you do some sort of blind estimation of the CSI by using some sort of prediction algorithm or something like that. Without preamble or without pilot, without known preamble or without known pilots, it's very, very difficult to estimate the exact CSI. You can measure the RSSI and everything, but measuring exact CSI is sort of impossible until you have some sort of known transmission that goes from the transmitter to the receiver.
I know, sir, you are running out of time, but
no, it's okay.
One of the participants is again raising a question and mentioning that one more last question from my side. And the question is, what role might quantum computing play in revolutionizing vehicular communication technologies?
That's a very relevant question with national quantum mission coming in, and a lot of initiative from the government side on the quantum part of it. So again, I haven't worked specifically on quantum computing applications for vehicular communication scenarios, but I believe so. So right now, if you see most of the work on quantum, although albeit there are some practical demonstrations as well, I'm not saying that, but most of the work that is being done is on the more of the theoretical side of it. And assuming the transmitter receiver is more or less stationary, am I right? This is something that is being taken into consideration when you want to send very high data rate through some sort of quantum communication methods. The problem in vehicular scenario, the channel is pretty dynamic. It's not a very static sort of a scenario. Am I right? The channel is something that is going to change more frequently vis-a-vis a normal communication scenario where you're moving with very low mobility. Specifically for vehicular communication, channel is more dynamic. To devising some sort of techniques that can alleviate this dynamicity of the channel will be something that is worth of research, I believe so.
So I guess, yeah, the participant is thanking you, sir.
Thank you.
And on the behalf of everyone present here, I would like to thank you. Your insights were incredibly valuable to us, and we are really grateful to you that you share your knowledge with all of us. Thank you so very much, sir.
Thank you. Thanks, Dr. Soumya.
And if you are comfortable, then you can share one of your contact detail.
Sure.
So that if any participant would like to connect for any further collaborations or maybe for some guidance, they can contact you. Even I can contact you.
Yes, sure. This is my email ID, and if you want to have this thing as well, these are two email ID that I can give. Both are. Oh, sorry. This is. I think I will just edit it. This is not correct.
It's okay, sir. It's okay. The first one is correct one, na?
Yeah, first one is correct.
vivek.b@it.ac.in.
Correct. Second one is schedule. Yeah. So instead of Vivek, I put Ike. So I think that is
Perfect, sir. Perfect. Because now I know that how will you remember all of the participants, but we can give you the reference of this FDP that we have attended your FDP and you were the speaker. And you
okay.
promised us that the gates are open for anyone
Yeah, absolutely,
in
absolutely, and
Triple IT
we are
Delhi.
yeah, absolutely. We are looking for good researchers who can contribute in our works, and I'm free to take more and more researchers who are passionate and really want to contribute in the field of study.
So thank you so very much, sir,
Thanks a lot,
and
Dr. Samita.
a very good evening to you, sir.
Thanks a lot, Dr. Samya. Thank you. Thanks a lot, and I hope the talk
Okay,
was
sir.
good.
Bye bye.
And bye. Thank you.
So we do have our next speaker for the session number 4. So I would like to, dear participants, you will soon receive the feedback link. Don't be worried about it. Just be focused on the talks because we do have such worthy speakers with us. And now Dr. Vishal Bhargav is already with us. So welcome and a very good evening to you.
Dr. Soumya,
Yes, sir.
am
If
I audible?
possible, can you please, yes, sir, you are clearly audible. Can you please turn on your camera so that
Done.
audience can, yeah.
Yeah.
So very
Okay.
good evening, sir.
Thank you.
And if you allow, can I introduce you to the participants?
Sure.
So, dear participants, session number 4 will be delivered by Dr. Vishal Bhargav. He is Engineering Manager R&D at MediaTek India Private Limited, Noida, India. He has received his PhD degree in Computer Science and Engineering from Delhi Technical University in 2023, and he has also done his master's from the same university in 2011. He has engineering experience with the semiconductor companies, ARM Holding, ST Microelectronics, and various startups. He has vast experience in the wireless technologies such as Wi-Fi, Bluetooth, NFC across different segments of embedded devices as mobile phones, laptops, gaming consoles, automobiles, and IoT devices. He has strong grasp of device drivers, firmware, and embedded applications. And additionally, he has authored over 10 journal and conference papers, and he has 4 granted USA patents on wireless technologies. So we do have Dr. Bhargav with us. So, sir, thank you so very much for joining us and for sparing your time for this session. So, over to you. The entire audience is with you now. So, you can
Sure.
start your, yes, sir, you can start your talk. And you are
Okay. Sure.
already presenter, so you can share your screen also.
Okay. Sure. Dr. Soumya, if you don't mind, can you give me a 2-3 minutes? Just I'm doing my
Yeah,
setup.
sure, sir, sure.
So sorry guys, just 2 minutes. Okay.
So participants, Dr. Bhargav will be back within 2-3 minutes. Meanwhile, you can also take a break if you want, but don't leave the session. We are here in the session only. And for the presentations and recorded videos, I have seen some queries in the WhatsApp group. So organizers will share the related content, the material, or whatever recordings will be there after taking some consent from the speakers. I hope you understand. So stay connected, stay tuned, and very soon Dr. Bhargav will be back. And if you have any queries from previous session, you can drop in the chat box. Meanwhile, you can drop in the chat box. I will collect all the queries and we will try to address later on. But stay tuned because Dr. Bhargav is in the session. Maybe he is getting, maybe he has got some call and he's attending that.
Hello everyone. I'm back. Sorry for the delay. Just let me know if you see my screen or not.
Yes, sir.
Is it visible?
Yes, sir. Your screen is clearly visible.
Okay, cool. So thank you, everyone. Ma'am, the screen, you can see that screenshot, right? The slideshow.
Yes, sir. It is.
Okay, great. So thank you, everyone. Thank you, Dr. Soumya. Thank you, Dr. Arvind. So good evening, everyone. And so I am currently working on the Wi-Fi industry mostly. So I will cover that part. And today we will embark the journey of the exciting world of the Wi-Fi especially for the IoT world. And as mentioned, my name is Vishal Bhargav and I'm currently working with MediaTek India. And it's my pleasure to work and opportunity to share the insight with you today on this exciting topic. And I am a manager on embedded software developer. So I will try to cover that perspective as well. And if anyone have any question, you can interrupt me anytime. I don't mind. So let's continue. So these are points I am going to cover: Wi-Fi introduction. I just attend last 2-3 minutes of last topic. So it seems it was also related to Wi-Fi. Correct me if I'm wrong. So these are the outline. I will go through the Wi-Fi 6 and then Wi-Fi 7, that is the new generation, and some like very basic embedded programming things so that programmer can optimize. Like currently that AI world is ongoing, lots of data is coming, but we need to process that data. So it's also that it increase the problem for the embedded programmer. So we need to solve that. And some patent I will cover, that how simple solution can put a big impact. Like it's not a rocket science thing, but how it can future trends. That's all. So it's a very basic thing. Like Wi-Fi is almost everywhere and it's expanding with her time. So the best thing is with Wi-Fi, it is a free band. Like if you are talk about the 5G or 6G, that is not a free, that you need to buy a license, you need to buy that frequency. But with Wi-Fi, it's a free band. So that's why it's a UVTX wireless standard and it can use anywhere. And it connects wireless things to the internet and uses existing infrastructure. You put a sensor like Google Home, Alexa, any other thing, just connect to your API and you can use. And the security is also increasing with the generation to generation. Wi-Fi 5 have some issue, but later that WPA3 came. So Wi-Fi 6 and 7 has more security. So that's the reason, that are some reason that Wi-Fi is widely deploying into the IoT world. So over billion of things. So this is the diagram I took from the Wi-Fi Alliance site. You can see the number of devices at around 3.5 billion devices, and these are the Wi-Fi certified device. Non-certified device also comes, but that certified, that Wi-Fi Alliance is an organization which give the certification, so people can use the Wi-Fi logo on their device. And with Wi-Fi 6, that is especially designed for reduce the power and cost reduction. So that's also enabled the growth engine for next generation. And after Wi-Fi 6, that new Wi-Fi will further increase the growth. So if we talk about the Wi-Fi, that why Wi-Fi now coming into the IoT. So that till Wi-Fi 5, that 802.11 AC, Wi-Fi have some generation I will cover later. So that only that is called the traditional Wi-Fi. That is only that time we are only focusing on the throughput. We are just increasing the data rate, how much throughput we can got. But that time we are not focusing on the other things like low power, latency, and so that is for especially and that is especially designed for the power plugged devices, like they are our laptop or the desktop computers system, and they are running on the Linux, Android, that high heavy OS. But for Wi-Fi or for IoT, that is different. Here the low power consumption is the main need, security, of course, security from the online and the physical attacks. And there is like a limited device resources. Like if you talk about a IoT device, it have very limited MCU. It don't have any MMU that have very limited memory. So that fully functional OS is not required. So that some specific IoT OS bugs, they are all without OS also device bugs. So and then cost and size constraint also there is a challenge, and that IoT devices generally work into the crowded RF spectrum. Even they send very little data, but they work into very dense environment like a factory, not shopping mall or airport. And that cloud connectivity also required. So these are some challenges for Wi-Fi. That's why that IoT thing is required. And of course that these things like if a small sensor or a small device, they don't have UI. So there is a limited UI option. Some need to run using the command line. Some need to configure by some Wi-Fi packets through the access point or the other things. So these are some challenges. So if I talk about the Wi-Fi usage in IoT application, so you can see this diagram. So why Wi-Fi is choose a best option for the IoT application? You don't need any other devices. You can use existing Wi-Fi access point and it can connect to your cloud or local WLAN device, anything. And all the IoT device like door lock, security camera, switches, NFC, or like that uh, QR QR related devices, LED bulbs, and home gateway, they can directly connect it to the your modem. And maybe that if, for example, some other devices like Zigbee, Z-Wave, BLE, or these are the IP based or non-IP based devices like Modbus, BACnet. If they require need to connect to the Wi-Fi network, then maybe you need an additional gateway. And these gateway have like they called the H gateway. They do the H processing. So they have some Wi-Fi like a protocol translator. So the protocol translator works here that can connect to your AP or modem. So that's how this Wi-Fi usage works into the IoT. And these are some advantage like why Wi-Fi. So in Wi-Fi 6 power saving capability, higher data rate is there. So for example, you need to update firmware of this security camera. So FOTA, like firmware over the air update, is something that is very tough for other protocols. If you like a firmware size is a some MB or it has a big size, like you need to upgrade the firmware of gateway. It can be in GB as well. So by you that much data you will download through the other protocol, that would be tough. But Wi-Fi, like with using higher data rate, that would be easy. So that's why that Wi-Fi is a great choice. And it also improve user experience. For example, some on IoT world that Silicon Labs and other companies working on this Matter protocol. So it's application layer protocol, and the other protocol like COAP, COAP, and MQTT, that easily like can fit into the stack of Wi-Fi or Ethernet. So that's why it also increase the user experience. And with Wi-Fi, like good thing is like you can do some simple provisioning on through the BLE. So for example, you connect the Google Ham, so that through BLE you send your Wi-Fi access to other device through BLE, and that device can connect to the your router. That's how work. So that is cover Wi-Fi usage in the IoT application. Uh, like we already, I thought we already, you guys already gone through the Wi-Fi thing. So this is the basically a Wi-Fi working. So in just a one line, like 802.11, that is Wi-Fi work on a CSMA that collision avoidance things, while Ethernet works on the collision detection. So simple thing like listen first before the talks. So I will skip this PPT. Anyone hand out, you can just interrupt me. This is a basic Wi-Fi connection procedure. So how a Wi-Fi device like a station can connect to the access point. So these are some phases like scan. So scan can be a active scanning or passive scanning. Passive scanning, just access point do the beaconing and that station listen for beacon. Or in active scanning, it send a probe request and in response probe response access point send. So active scanning is the faster, but passive scanning save your power. You don't need to transmit. You are just set into the receive mode. So that save the power. So it depends on your usage. You can use a hybrid as well. And these are the connection procedures. So authentication, association, and this security establishment in four-way handshaking. The thing is like Wi-Fi connection procedure is still the same from the first standard. That first standard comes into the 90s and till now it is the same. So these are the Wi-Fi evolution. I am only covering from the Wi-Fi 4, that is 11N, and then Wi-Fi 5, 11AC, that is, this is the Wi-Fi 6 generation, 11AX, and the Wi-Fi 7 that is still in under development, and even the full spec is not released by the IEEE. It is the in draft version. So we will mostly cover on this Wi-Fi 6 generation and Wi-Fi 7 generation. So we will see like what is the advantage and how it goes. Here only the focus is on the throughput increment, and other things also came. So Wi-Fi 6 that is dedicated design for the IoT world. So these are some like what Wi-Fi 6 can bring. So it is addressing major pain point of till now whatever the Wi-Fi is going on. So in the era of 11AC, that is Wi-Fi 5, the requirement of capacity, connectivity, and latency and the low power are very relatively low. So that to solve that problems, and especially that roaming problem, and for example for low power, that IoT problem, that Wi-Fi 6 evolved. So this is like, sorry. So if I talk about the before that Wi-Fi 6, like there are in a campus network, whether it's a college network or it's a company organization network, there is a dedicated wireless office network, the dedicated IoT network, then the dedicated video surveillance network is used. So it has so many drawbacks, like if something is happening, first thing is like the cost is increased, like that maintenance cost or the development cost goes increased, and there are so many interference happen between the different wireless network environment. If something is if both are work on the same channel, and sometimes that load balancing algorithm works, so this come on to the channel 36, and if this is working on channel 100, but some radar detection is happening, so that also moved onto the same channel. So much interference is happening. So that solution is like with Wi-Fi, that co-site and co-vac hello of IoT networks comes, and which reduce the total cost of operation by the 50%. And this data I took from the Hawaii, that is they publish a white paper that how this TCO reduced by the 50%, that I have also put in a link into the reference that you can check that. So that co-site means that physical location for that deploying Wi-Fi access point is same across that all IoT network, that video surveillance network or wireless network. And that backhaul means that they are using the same backhaul, that network connection into the background of local network. So that also why it reduce the total cost of operation. Okay, so this is before Wi-Fi 6, that there is a passive response, that that operation and management, that with Wi-Fi 6 there is a proactive operation and management platform developed, which was not available before that. So IoT world that believes that in Wi-Fi 6 it is necessary to build an active operation and maintenance management control and analysis fusion to achieve minute level fault location. So for example, that with this closed loop, any fault is happening. So that is it's there is a centralized configuration and monitoring of device developed using the cloud, and that fault detection is on the dynamic. And there is some AI algorithm also work. Like for example, I show you the Wi-Fi connection procedure. That is like Wi-Fi work in a very sequential manner. So that, for example, like something has happened that associate that authentication is happen, association is also happen, but you stuck into the four-way handshake. So using that telemetry, that it can either check you at the debug log of your wireless access point, or it can decrypt the sniffer, that is sniffer capture, that is using the Wireshark or something, so that a AI algorithm can detect like, oh, that association is fine, but that it stuck into the four-way handshake, or maybe possible that that four-way handshake also passed, but that it is stuck into the DHCP things. So like the network, one access point capacity is full, the 255 the limited capacity of IP, it can give only 255, and there is a more than that device is connected, or either that other device is disconnected, but the lease is not released. So these AI algorithm can help us to detect the fault into the runtime. So why Wi-Fi 6 is very famous, like how it helps for the IoT device. So these are some key features which come into the Wi-Fi 6. So first one is the full duplex MU-MIMO, that is multi-user, multiple input and multiple output. So before, like in Wi-Fi 6, there is an MU-MIMO, but that is not full duplex. That is on the single direction, and there's only 4x4 support. There is like four antenna in a go, but Wi-Fi 6 double that capacity, that instead of 4x4, that is physical layer reach to the 8x, and it's a full duplex. Like not only the downlink, that uplink also supports there. So that it allows the station to send their acknowledgement or other packets to the AP simultaneously. So it saves lots of air time. And same like beamforming is also there. So to enhance the parameter, so you can, that access point just send a data into the particular direction. For the like denser environment, like lots of devices working onto this, not your access point, not your basic service set, that other basic service set also come into that environment. So that time OFDMA and that BSS coloring is help to increase the network efficiency. So BSS coloring is just a means, like every BSS means like my company MediaTek, like it is in a building, like in same tower some other company was also there. So the company B is also there. Their access point also overlap into the our environment. So that the coloring term is like you give a unique identifier to your access point, so it works on this frequency. So other AP can detect like it is working, it is using the same coloring, so it can go into the some other frequency or channel. So that's how it like increase the efficiency, and there's less collision into the environment. And for to challenge that longer battery life, that is more must awaited things for the IoT devices, because the problem was with Wi-Fi only that it consumes lots of power in compare of other things. It provides the advantage, but it takes a lots of battery. And that power saving mechanism, like whether it's a legacy power saving frame like PS pole frame is used, or the null frame is used, from the first standard to the Wi-Fi 5 it was same. So like there is a DTIM frame sent by the Wi-Fi access point, so every device need to backup at that time. And when we say that device is backup, So Wi-Fi devices, it have their own MCU, it have their own processor, so that whole device, like the clock, the MCU wake up, that it works on the high clock, and the complete the RF chain is open, so it takes lots of power. So that TWT, like here, station or AP can decide when it will wake up or when it can go into the sleep. So that's why it save a lots of power. And this we will discuss later in next slide as well, like how this TWT works. So and or after TWT, there is a like to increase the coverage or longer range, that is also increase the guard. It like earlier only there is one guard interval, that 0.8, that short guard or long guard. But in with Wi-Fi 6, there are the three guard interval introduced, so that data can send to into the longer range, whether it's happen any reflection or something, so that that it for receiver it is easy to parse that packet. So this is the TWT. So TWT is allow device client and the AP to negotiate specific times when the device will wake up to transmit or receive the data both. So during that time, other device can remain in low power sleep state, and it can conserve the energy. So uh, if I talk about the old power save, there is like in every beacon there is a or DTM frame that you station divides need to awake when this beacon come and other beacon came, so it need to wake up to see that if there is a packet is available for me or not. But here not the case. Like when AP send the trigger frame, then only the station will awake, and it's like AP have the centralized control, so it easily can give that okay, you have the packet and I am giving it. And even API control that if have a packet for 10 station, but it only can give the packet to 5. Like I don't have I have packet for the first 5, and later I will attend the other 5. So that also the feasibility that TWT gives. So there is in TWT, there is two type of method, individual and broadcast, both types. So each device can negotiate there is sleep period with AP, and broadcast TWT, AP provides sleep period for group of device. So both method is there, and there is a like what happened that it is not like that any value they can use. There is a negotiation is happened. So the backup time, like that is they have negotiated that duration time is narrated, which frequency they will use, like how often uh, they will devise the backup, and later that negotiation also closed by the device at the terminate session or frame also exchange. So these are the Wi-Fi management action frame generally used for the check for negotiate the TWT. And with Wi-Fi 6, OFDMA also comes. So that is for the better spectral efficiency and capacity. So we know that OFDM is modulation scheme. That actually both are the modulation scheme used on the wireless communication. But OFDMA is introduced into the in with Wi-Fi 6. So here, like in OFDM, that particular subcarrier is decide like station when can use the this particular frequency, and user 2 can use this particular frequency. But with OFDM, that subcarrier channel divide into the smaller unit that is called RU, that resource unit, and that AP can decide like which group there are. Actually, there are group is created. So, for example, group 1 have the uh, frequency 1 and frequency 2. Group 2 have the frequency 3 and frequency 4. So AP decide that which station will join that particular group, so they can share the data on particular frequency. So that allow Wi-Fi devices to 100% like high percentage use of the environment and with the less congestion. And actually क्या actually problem issue with like IoT device, they have very small packet. For example, you wear a watch that only what it send. It send your heart rate, it send you the sleep time or some. It have very small data. So for small data, this method is very good, and it provide the multiple sub channel to protocol to secure small data packets. These are some example. These also I took from the Hawaii white paper. So they put like Hawaii builds Wi-Fi 6 based global digital office. So it support like 15,000 HD smart screen, and they are whatever the number of billion message they are sending, that email, that video conferences is ongoing. So they use Wi-Fi 6, and they show that how Wi-Fi 6 help to use their network 100% with full capacity and with less consumption of power and latency. So this is also like so many AGV, that automated guard vehicle is working on factory, and their firmware update is happening through the access point. That is also very uh, that is very easy, and other devices can work, and they are not like with Wi-Fi. There are Wi-Fi 5, there are lots of disconnection is happening, but with when they put the Wi-Fi 6, there is very less of number disconnection, and they reach to the even zero to maximize the capacity. Same example. So Wi-Fi 6 came into the 2021, but still it is in like a deployment phase. Even if you see in your company or your college, university, either the access point is Wi-Fi 5, or now they are deploying the Wi-Fi 6. Now Wi-Fi 7 is also on door. We have developed the things that certification is already coming, that draft version specification is also there. So let's see what is into the Wi-Fi 7 things. So these are the some feature lists. So the most important features came into the with Wi-Fi 6, that is by MLD, the multi-link overlap or multi-link discovery. And this Wi-Fi 7 is come for the extreme high throughput. So with Wi-Fi 6, that ideal throughput at 9.6 Gbps, but with Wi-Fi 7 we are reaching ideally by 40 Gbps. And they also increase the security with GCMP 256. So that is Glossius counter mode protocol. So which have the 256 key length. So basically it's a cryptographic protocol used for secure communication in Wi-Fi. Multi-level discovery. So till now, like for example, you have access point at your home. You can see that you have two radio or 2.4 gigahertz or 5 gigahertz normally. And if you have a Wi-Fi 6 AP, that it have a 6 gigahertz also comes. So you can see three SSID. That one is on 2.4, that one 5, one on 6. But currently with till Wi-Fi 6, you can connect with your phone, only can connect either on any link, not on the simultaneously. But that multi-link with Wi-Fi 7, you can connect your phone on 2 or 3 link, depend on your phone configuration, whether it's a 2x2 or 3x3. So that is the multi-link setup which comes into the Wi-Fi 7. So uh, there are like a procedure, multi-link discovery procedure. For example, I have the access point of Wi-Fi 7, which doing weakening on 2.4 gigahertz, 5 gigahertz, and 6 gigahertz. It's a because AP have the 8x8 radio, so it don't have the problem. So, but your phone find a beacon that it's a supporting the MLO. So you and your phone is 2x2, so you can connect either 2.4 plus 5 or 5 plus 6 or 2.4 plus 6, depends on your phone configuration, your country availability. For example, in India, that 6 gigahertz some is not available till now. Still that IEEE is talking about that thing. So, and 2.4 gigahertz, lots of devices work on that. Bluetooth works on that. Your microwave works on that same frequency. Even that by USB 3 also works on the 2.4 gigahertz frequency. So on which 2 or 3 link you want to connect, you using multi-link discovery a setup, you can decide. And there is like you are transferring data on to the ring. So that block X is instead of every packet acknowledgement that you can decide like 32 packet you will do acknowledge into one go. So it also increase the throughput. So that block X comes into the 11N, but that multi-link block X come into the with Wi-Fi 7. Link management with default TID to link mapping. So you can also like decide TID. For example, Wi-Fi have provide the QoS functionality, the quality of service. So it divide data into the 4 types of category: that best effort, voice, video, or background. So for example, you are talking on someone on the Wi-Fi audio. So voice have a highest priority in comparison of other TID. So you can decide that particular TID like 6 gigahertz have very less interference because now very less device on that. So you can decide that your voice category packet goes into the 6 gigahertz frequency and other packet goes into the 5 gigahertz frequency if you are making connection in 5 plus 6 gigahertz MLO. So these are some like MLD level sequence, or there are different sequence. For MLO, different power management comes, and BSS parameter. So there is a like a critical update procedure available also. So for example, you that something is change is happening on 5 gigahertz SB, so that it can send critical update on the beacon so that BSS can update according to that. There is like thing MLD operation in non-AP. Non-AP means station. There is a MLO have some type we will decide, but STR only mandatory support for the access point. And in access point, if I were to talk about the access point, there is a mandatory support. Even if you are supporting MLO, other devices not supporting MLO. So single radio non-AP support it's also required. And there is a mode of NSTR that I will discuss later. So there is STR operation is also mandatory. These are some operational feature. Earlier one was a mandatory, but with Wi-Fi 7 there is a like you can increase the block X bitmap to 512 so or 1024. So you can give the acknowledgement of 512 or 1024. So sliding window protocol that works according to that bitmap protocol. There is a restricted TWT. So in Wi-Fi 6 that TWT comes, but that restrict like it only give that particular duration you can use. But here there is they have removed that restriction. In TIT to link mapping negotiation earlier that mandatory optional they have put that in runtime also that you can change the TID to link mapping. EMLSR mode. So this I will discuss later, like MLMR mode and thus other things. So I like I already talked. So faster that the throughput is around reaching to 36 Gbps. Latency also decrease, and with new MLO like with MLO you are always in connected mode. For example, you are working on the 2.4 gigahertz plus 5, but 2.4 is so much noisy, but you will still connected on 5 gigahertz. You are keep alive packets that a session will send to the AP that is going on to the 5 gigahertz. So you will that your device especially will connect in always on connected mode. So these are like Wi-Fi 7 technology. So that they have increased the modulation to the 102.4, 1024 to 4096. They have also increased the bandwidth. And this is the MLO, so which I talked about. So with Wi-Fi 6, you can only make a single link, but with Wi-Fi 7, you can create a multiple link to performance improvement. And this like there are some modes. So we will talk about how it increases the throughput or how it improves the latency or reliability. So actually this is the earlier like specification expected to publish by late 2023. So it came, but it was the draft version. So and Wi-Fi Alliance recently developed the certification. So they have finalized, but still they are adding some tests. So Wi-Fi Alliance is also an organization. It's a different from the IEEE. So they check that whatever is covered, that device is supporting or not. So they put a certification. Any device does not take any, for example, you have data, like you are downloading the data, but it's a normal data, background or best ever data, but you are using always and using the voice category. So what happened, your station performance will increase, but you will ad hoc the network, so other device will get less chance to send their packet. So Wi-Fi Alliance put a certification to check these type of thing. Our device should not take the advantage of this feature. So they put like they generally put give the data of background or best effort, and they check how much in you are not supposed to send using the voice or back video priority. And MLO is the one of the key feature that I already discussed. So MLO, this is generally like how it works. So we are sending the concurrent data device, and like if you see the difference between Wi-Fi and Ethernet, there is difference only the two layer, MAC layer and the PHY layer. Per layer are same is completely. So that's why it only show that we are talking about this IP address and to the only the station MAC or PHY layer. So to upper layer, there is no difference. Like if you see, if you do the IP config, or so you, for example, in Windows, if you see the MAC address, you will see only the one MAC address. There is not like here two link is there, but you will not see the two address. But internally, that for example, this MAC A or it can be like MAC B. So internally, there is a two MAC address or three MAC address internally will work, and again that data will collect or combined here, and it is given to the upper layer similar to the old things. So that's how this packet level aggregation will work. Even that MLO increase the throughput, but its main goal is to increase the reliability, not the throughput. Because if you see our internet connection, my internet connection is 300 Mbps. Wi-Fi 6 was enough. Like even no one is using 1 Gbps or 2 Gbps downloading. So the main concept to increase the reliability, they put a concept of MLSR. So that multi-level single radio. There are multi-level things, but only one link it active at a time when this transmitting. So that's how this extended MLSR comes. So what it put that device, like it's a 2x2 device or 3x, it listen on, like it will receive packet on every link. So that there is a suppose three antennas there, the all three is listening there, but when they transmit packet, so they will transmit only either on 5 gigahertz or the 6 gigahertz thing. So that's how MLSR works. This is the MLSR. Or STR, that simultaneously a TXRX or non NSTR, that both 2x2 works there. But this is like expensive things. Well, I don't have any diagram. Maybe I'd have diagram. Okay, no worry. So I will let you later that how this. So this is for the expensive hardware. Like 2x2 antenna on 2.4 gigahertz, on two antenna on 5 gigahertz. So good for the access point, but not good for the station like your mobile device or IoT device. So generally they use the EMLSR or MLSR things. And I also give a link of this MLO white paper. So this is a MediaTek white paper developed on MLO thing. So you usually can, if you usually do Google MLO MediaTek, you will get this white paper. So here all the modes is defined, that how asynchronous and transmission modes work. So this NSTR, that is like, for example, both devices transmitting, but they can also interfere each other. So what no, NSTR device, what they pause for some time. So the first device, first radio transmit first, and then later the second radio will transmit. So how it save the interference. We have time, so I can go. Maybe. Okay. So MLO allows for band switching and load balancing, for example. So for example, initially you connected to the 5 gigahertz and 6 gigahertz through your phone. Now Pixel and even new iPhone came with Wi-Fi 7. So you can connect, if you have the access point, you can connect using the MLO. So suppose that 6 gigahertz and 5 gigahertz you are connected, and 5 gigahertz goes very bad. There is lots of device came into that, somehow that it is not useful to use. So on runtime, you can switch the bit range, so that there are Wi-Fi 7 provides some frames, so access point sent to the station, that you can jump to the 2.4 plus 6 gigahertz now. So it adds out, it do the load balancing. And that there is a like in that white paper, or that EMLSR delivers 80% throughput environment in dense environment. When your device only support it don't support the STR, but it support the MLSR. And EMLSR achieve 85 average latency reduction in high network condition. Of course, it's increased throughput and lower latency, and it increased on same things, like it improved network reliability and performance, and it also enhance user experience for real-time application. So if you are connected to MLO, like downside, whatever your devices is doing, like it's jumping from one frequency to other frequency, but it does not impact on the user. You are watching a movie on Netflix, like it will work smooth if MLO is there. There's no such issue. So these are some simulation we did to achieve this thing. So it show like we run the throughput test. So there utility, very famous utility IFOF is there. So we use to do this throughput test, and we run the FTP TCP traffic. And to the latency test, we do the like bidirectional video conferencing using the Zoom application. So that use the UDP traffic. And this is the configuration of a different AP. So we use the single link station. 80 fire rate, we have all these things. So this figure, like this figure show that we have the network elements include an APMLD, that access point MLO, that support two link. Just for simplicity, we put only two link. And these are non-MLD, like these are legacy station, and this is the MLD duty, which have both link can work simultaneously. So no one MLD, the two non-AP MLDs each link with AP MLD is used to generate background uplink traffic, UDP traffic. And so, and if I discussed about this mode, operation mode and configuration, so we are assuming that APMLD can fully support two NSS, TX and RX. So there is no need to switch NSS when the peer STMLSA mode operated into the MLSR mode. So this is the like our hardware thing. So for example, here, for example, like we develop the Wi-Fi product. So we have every type of customer. Some need us cheap solutions, some need a little better solution. So this is like here we are describe the implementation of quad antenna, 4 antenna station for different amyloid types. So left side figure example an NSTR, there's known STR or EMLSR type, and right side figure which have the isolation. So for the small form factor station such as mobile phone, option in left figure may be preferred due to the front end complexity consideration. So depend on the use case, what type of architecture is used. And these all tests not done on using any simulator, all real access point in the station taken, that all are MediaTek solution. So these are provide like whether it's a single link station, NSTR, STR, or EMLSR. So we have comparison of we did the comparison of throughput. So and these are different. I already show them different loading like condition in different network loading condition is there. We download so much data. There is FTP is ongoing, some video conferencing is ongoing, and other thing. So we can see that EMLSR has the best performance when network becomes more congested. Like we are increasing the congestion in the network. So like when the 70% congestion happen into the network, that is still that with EMLSR we are reaching around 370 Mbps. This is because EMLSR can utilize all NSS for transmission using the link with the least wireless condition. And the result also show that NSTR has the burst throughput. This then other as difficult to perform simulation transmission in the uplink direction on both link when one of the AMOLO link is busy, because NSTR there is an interference between two radio itself into the device. And this is the calculation for the Wi-Fi latency. So here also like you can see that EMLSR is clear winner with STR, but STR hardware is costlier in comparison of EMLSR. So this is measurement is done with 90% congestion. The results show the latency of Wi-Fi 7 MLO station can be improved from 145 millisecond to 80 millisecond. Yeah, 145 NSTR and sorry single link and EMLSR 80. So it's a like around 85% improvement in comparison of Wi-Fi 6 single station. So it also show that STR have the lower latency equal to the MLSR, and NSTR at little increment in comparison of both. So these are some system architecture is used. So these are 4 architecture is there. So we use the open WRT for development the access point, and like MAC, this MAC layer is also divided into the upper MAC and layer MAC. Host is the upper layer stack, so it comes all the like from the data link except MAC, that the network transport to the application layer, that host things come to the into the this host or application layer. So these are some architecture which used by different AP vendors or different Wi-Fi chip provider. Maybe we can go like brief discussion onto this. So the 2-tier, like when we divide into the this UMAC into the MAC into the 2 layers. So 2-tier MAC implementation enables frame to be transmitted simultaneously over multiple links. So UMAC is the common part for the all interface which performs link operation. If I talking about the only UMAC, so it buffer the traffic from the host before it assigned to the specific interface like a to our radio. So it just buffer the data, and it also buffer in packet from the different direction before passing to the host layer. So the UMAC also enables seamless transition between links to minimize the access latency for efficient load balancing. Uh, so if I like that PSDU or MPDU, if I discuss low, that MSDU that comes from the this upper layer, and the MPDU is given to the MAC layer. But here like aggregation is happening on upper layer, and that uh, the data is just transmitting from the PHY to directly to the, or if comes from the OS to the PHY layer. That is architecture 2. That in architecture 3 we have moved that MPDU aggregation into the LMAC things. So here that dispatch is happening on the MPDU. M is for the aggregation that multiple like in Wi-Fi that you can aggregated packet that on MAC layer and file layer as well both. So that multiple PDU and the multiple SDU that is there. So this is the architecture base. So here interchip bus is there. So architecture 4 is more like a distributed solution. So because that MSDU aggregation you are doing on the UMAC and the MPDU aggregation you are doing the LMAC. So this is the highly efficient architecture in terms of throughput and the latency, because you are not when the things go to the upper layer, it takes lots of time, and these layer bugs very slower than in comparison of other layer. And you guys heard the term of hardware acceleration. So these things can develop into the hardware instead of software, so it accelerate the performance. So that's all architecture currently is using by different chip vendors. It also depend on like what they'll what type of solution is there. If there is like RTOS based or some real time requirements, so architecture for. But if that there is no need of this thing, so and the more decision taken on the application layer side, so architecture 2 or 3 can be used. So depends on that. So this is the difference. I already talked about like so what are the item and what architecture. So but the architecture for is little complex, and it needs MAC memory for TX description. TX descriptor is like for MAC layer. MAC layer don't know where to send the packet. So before the Wi-Fi packet MAC header, that TXD is added by the upper layer, which is understand by the file layer or the basement thing, where need to send the packet, how much the size, whether it need acknowledge and other thing. So that memory goes increase for the architecture force. So it's complicated, but have a high impact on power consumption and cost. Of course, cost is matter. So I talk about lots of about Wi-Fi 6 and Wi-Fi 7. So we have already discussed all the things like what bandwidth and so sorry, this is the typo, this is device density. So which is better? So Wi-Fi 6 is like Wi-Fi 7 companies is spending so much, so they need their R&D cost also return. So Wi-Fi 7 AP this time is very costly. If you see on the Amazon or the, you will find that is very costly. So Wi-Fi 6 is best for the cost-effective, low power, low bandwidth IoT device like its smart sensor, wearable, smart home system, and other thing. But Wi-Fi 7 is ideal when you use ultra level of low latency. You always want to connect, you never want to disconnect, high speed transfer, and there are so much dense environments for industrial IoT, smart cities, or robotics. So my recommendation is choose if like for example in university or in a company, if you are working on a general IoT application, so focus on the cost or efficiency. Instead of Wi-Fi 7, use Wi-Fi 6 router or devices. But you want to develop some ultra low for a smart city where your traffic signal is talking too much and they have the data, huge data, like so many cars are standing on the traffic signal, and you want to send to data to the other traffic signal. So that if that much of data is transferring, so you can opt for the Wi-Fi 7 as well. You can solve that traffic problem using this kind of approach. Some machine learning algorithm put on the traffic signal. Even Google is working on that thing in Bangalore. So I talk about lots of Wi-Fi specification. So generally what we understand like Wi-Fi device, so you see your phone, your laptop. So this is right side, there is a link like in your, if you open your laptop, so you will find a Wi-Fi card, whether it's Intel, Realtek, MediaTek, any AMD. So it's a PCI based card that generally Wi-Fi card plug into the by a PCI interface. And for example, if you have old laptop and you want to upgrade your laptop or desktop using latest Wi-Fi 6 or 7, so you can use some dongle. So that companies D-Link, Netgear provide this type of dongle. So this is the USB based dongle. So this is just a diagram to understand what Wi-Fi things is working. And these are the some architecture. So left one is work on the Windows side. So Windows is more complex in terms of for developer, but for as a user, it is a simple one. Why it is complex for developer? Wi-Fi security, Wi-Fi security, and some other things like supplicant things managed by the Microsoft, and it does not provide you the source code. So it's not open source. And kernel mode, there are like concept of managers. So these are different object of operating system. So that user mode can talk to the kernel mode. And if you talk about the Linux architecture, so this is the Linux architecture. Wi-Fi have three type of packet actually: management, control, and the data packet. So data packet goes through this path. So there is a IOCTL, that system call interface used, some socket is used, and that management packet goes to this utility. So that CFG, that is different type of architecture, that open MAC or it's a closed MAC. So management frame, that is or connection related frame, that go into this path. And this data path is common for the Ethernet driver. And so till your chip, like I show that chip is plugged into the laptop, you receive the Ethernet packet, then you need to convert that packet into the Wi-Fi packet and you will use it. But in Windows, it's not case. Operating system take care of that thing. You will get Wi-Fi packet only if you are using Wi-Fi things. So uh, now AI thing is ongoing. Everyone is moving AI. Lots of data, lots of things. But at last, that hardware need to process that data. Whether you are using so much data, uh, any library, any good algorithm, but lots of data is coming to the for the embedded program. So they need to still we are using embedded programming. They need to you optimize their programmer. So I cover like why we need to cover this thing, because first thing is like interrupt handling. That packet come into the PCI, that lots of packet is coming to your PCI interface. That is So if PCI just interrupt your, I show that PCI device plugged into the laptop. So that is interrupt. PCI works on the interrupt driven protocol. So here packet come into the your RF, that you come to your hardware, your firmware, then you need to send to the your host, that is operating system. So interrupt come to the your host side on your operating system. So efficient interrupt handling is essential to minimize the latency and the maximize throughput. So programmer need to ensure that Wi-Fi device driver or any device driver, not Wi-Fi, that Ethernet, your graphics device driver, to handle interrupt effectively. So you need to prioritize critical event. Just for example, such as you receive the packet, so you can't put all, like that is something is working on the critical section, but you can't put large code into the spin lock that it can break your thing. So that's why embedded program need to worry. They, of course, you optimize data path. So like for example, that where management packet needs to send to your firmware is like a MCU, but data packet directly can send to the hardware. That hardware acceleration just send the packet. They don't need to parse through the firmware. So that optimized data path is required. Power management, so efficient, of course. Power management requires to minimize the power consumption and without sacrifice the performance. It does not mean you are saving so much power, but you are not sending the packet. So low power, you need to optimize your low power mode during ideal period and optimize the transition between power optimization to minimize latency. For example, that there is a mode into the Wi-Fi or Ethernet, that beacon Ethernet or beacon wireless LAN, where what happened that your host part, that operating system goes into the sleep, but your device awake, and it only replies some packet. So that you need to optimize that. If some garbage packet comes, that hardware can just drop that. You can filter that packet. Does not give to the your MCU or just process that thing. Quality of service, that you need to prioritize the traffic, that voice packet goes fast, video later, that other, so that real time application does not impact this thing. Firmware optimization, that firmware running on the Wi-Fi chipset, so use some AI algorithm or other things, so it optimize the things, that latency is reduced, and identify the bottleneck, that your command, for example, that some it only not only the data, some commands also need to give to the hardware at some time. So you need to prioritize that thing, that whether command is important or data is important. So you optimize firmware. Driver profiling and tuning. So profiling and tuning is something like you do profiling of your code base, so how much time it is taking. Like it's like a very old thing, like you don't use so many long switch things, so break that switch into the smaller switch, and always do that profiling and tuning. There is a scope. Don't use much large variable. Don't put so much effort on the MMU, that your code is doing so much malloc and the free operation, whether it's not required. And use the offloading and hardware acceleration. So offloading means like, for example, in one feature, like there is a like 4 packet into the our Wi-Fi connection authentication, authentication request response, association request response, and 4 packet is DSCP. So there is a one IoT very small packet. So in IoT project, we have offload that DSCP into the MAC layer. So it does not go into the upper layer. So it's that's how you can offloading really neat thing. And don't rely. Sorry. Okay. So don't rely on the old OSI layer thing. It does not mean like you can offload some application layer work to the MAC layer or file layer if you can do that. Your hardware is allowed, so you can optimize that thing as well. still that embedded world, like whatever we return device driver or firmware, mostly 99.5% is in C. Some part is an assembly language as well, but basically C is still the major language for the embedded programming. So I'm covering this thing also, like you can see that lots of semiconductor boom is there. So of course that hardware design engineers, they are required, but VLSI and these things. But that software programming is also needed when it's required. So that's why I just covering these things, optimize things. So today that compilers are very good. That compiler optimization is also a field that they are optimized. Like for example, they don't leave the uninitialized variable, and they detect the static code analyzer issue, so other things. So they are very optimized. But however, some cases still there that uh, programmer can help compilers to generate the better code. So I am covering some techniques which can programmer use, so that whether you are creating programming on Android or desktop or for server application, so that will help. And I'm taking the example of ARM processor because generally x86, x64, that is like use only till the laptop or some servers. But the Android processor, the ARM processor is everywhere, on every phone, every handheld device, IoT device, and everything. So generally, when we do study this restrict keyword, that is we don't use in when we write a program, but basic C code just written for the general purpose computing. So it need optimization before is used in for the machine learning thing. So machine learning engineer, they are doing like they are optimizing their Python code and they are using the NumPy library. But what about that data is, even you are writing the something into the your hard disk also. So their file system device driver also comes. So they also already written into the C, and that working on the with limited memory, processing power, and power budget. So when a compiler auto vectorize means the peller process the code. So the compiler automatically transform scalar operation into the vector operation. So this restrict keyword used to use the SIMD, that single instruction multiple data capability of modern CPU, to improve performance. So uh, this is just a simple example. Even this is available on a ARM processor, that white paper on ARM processor white paper. So it was just taken from there. So before we go into this restrict keyword, let's first demonstrate this problem. So just consider this C code. Okay. So there are like 2 point scale vectors. That function is important function is scale to vector by the same scale vector multiply by C. So this is like just a same vector, like a vector where overlap this value is scale vector is overlapping with the B also. So AI you are doing, and BI, that is also that doing the same operation. So I also generate this assembly instruction, which is generated while I run this program. So here, like just we give the input, like and after that operation, that it just multiply with that value. So what happened that if we see this assembly code, that so the deassembling code, that it has no, like the function has no way of knowing that what argument need to be called. So we say 8 instance of multiple, like if you count that multiple, that there is 8 instance of multiple there. Whether even these are the operation are independent, they can go simultaneously, but but still there is a, we can see 8 operation. So, and same that LDR or that number of loads and stores also indicate that CPU spent too much time waiting for data to arrive into the cache. So we need a way to tell compiler that it can assume that buffer passed are the independent. So that's how this restrict keywords works. So I just use this restricted keyword into the my solution, and you can see that's assembly instruction. That LDR and that load that change to the LDP sorry, I forget the number, like, but you can see that earlier there is a like 32 instruction there, but it reduced to 17 instruction, and there are only 5 loads and 4 stores there. So that compiler know that these operation can do parallelly. There is no dependency on that. So using that restrict keyword, you can tell compiler. So this is the one way, like, and for example, that I also took a memory latency thing. So that this data is taken from using this link, that it put if data is in LV cache, so how much nanosecond it takes. If N2, then how much time it takes. So there's memory latency. So how that memory latency can solve? So for example, you are working on some IoT project, and you took some embedded Linux or FreeRTOS or any simple RTOS or a small embedded OS that is developed by ARM using your development. So here, like, what is happening, that node is taken, that you are doing every time this new node is doing, you are doing the malloc. So when you do the malloc or free operation, that MMU unit needs to work. So it need to make up that cache, the paging table, and there is a dictionary or some high data structure it need to use to check the indexing. So which part is free, how much memory you take, whether it's congested, continuous or not. That so MMU play the role. So if you calculate latency in this function, I have created there is a 10x nodes into this example. So and this is the this data you will get on the Linux. There is a command inside the GDB, so you can print that latency number of every function, how much time that malloc is taking. Like, so it will give that 24.62% is taken by the malloc, and you can also do profiling. So this how much time the program runs. So when I create this much of node, I found out that 29,000 something microsecond is used. Now what we did, like in IoT, that you have the memory. So instead of always do the malloc, you can allocate memory in a one go. So for that particular node, you have assigned a memory on malloc one go. That's simple, that allocator size. And when the any node is required to memory, I am just giving the memory using this simple alloc things. I'm not doing again malloc and this thing. So here MMU is not playing any role. It's a simple allocation thing. It's generally followed by the embedded programmer. So it takes it saves so much time. Like if you see that earlier there is a 29,000 something, like it come to the 5,000 microsecond. So it's a 20% of time, and you can still get see that which function is taking. But it is like the data is just to generate 100% of how much overhead is taken by which function. So that's how you can save so much memory. These are some other points which need to take care by the uh, programmer, like memory alignment, use proper locking mechanism. Don't if there is a need, then use the lock into your code. Don't use code just to like protect your data, and whether it's a spin lock or other type of lock, uh, like for any like a mutual exclusion or something. So use proper locking mechanism, uh, and use maximize bitwise operation. leverage integer versus floating point thing, auto vectorization, and modify loop. And ARM architecture has a plenty of great feature that when used properly can significantly improve your programming. So ARM, you will find that ARM for IoT, ARM for machine learning, you will find so many features that they have provided to just to increase your program throughput and it work, how can it work faster. So people can do also like if you are using Cortex M33 processor or something new processor, that is the document is available. I put some very simple patent here, like which we filed earlier, but that is not a big problem. But like it's not patent is something like you guys write out so many journals. I feel that is very challenging things in comparison of patent. I assume if someone can write a SCI journal, he can put at least file 50 or 100 patent, even US patent, not Indian patent. So this patent we just put a like a, for I discuss a one mode that is back on wireless mode. So I use the like when we access point also have some other wireless network protocol available. Not only the Wi-Fi, it can have a Bluetooth, GPS, and BLE, Zigbee, and other thing. So that we use a single communication protocol to connect our network. So what we did that Wi-Fi and the Bluetooth both are connected with the access point of like access points Wi-Fi and Bluetooth with stations Wi-Fi and Bluetooth. So if there is a small packet and you don't need to make the whole Wi-Fi device, just send that packet on the through the BLE or Bluetooth if it can come into that. So it saves lots of power of your station device. For example, that in that wake on wireless LAN, that is that device does not go into the full power save. That half device host is in sleeping, but still that your firmware part is broken. But using this communication protocol that if like for example there is only a EAPOL key reaching or the only ARP resolve packet is there, so you can send to the Bluetooth or something. So that's how you can increase your power communication, and that also help into the old Bluetooth, old Wi-Fi power save mechanism. So station does not need to wake up on the DTM thing, other thing. So that's how that even that for example you put your Wi-Fi phone when you are sleeping into the sleep mode, but still it need to awake sometime and it send the access point keep alive packet. We say that some packet that access point I am awake, don't disconnect me. So but if that packet can send through the Bluetooth or BLE, it can save in a night, you can save lots of power. So it's a simple like this is you will find that network connection and maintenance, that very simple idea, but that is very useful in general scenario. For example, this idea I also patented some years ago, 2-3 years ago. So in generally we traveled Taipei. So Taipei is a city where so many Wi-Fi access point is available, and that is free. But problem is like some access point don't have the internet. But what happened? I need to connect to every access point. I see that whether it's the internet is available or not. Not only the internet, that whether what is the speed of access point and what is the latency is it is providing, that is not available to me. So I connect the access point, then I do the Google, it does not work. I type some other site, still it does not work. Then I find out that, oh, internet is not in this access point. So again, I connect to the second. So it's so much waste of time. So Wi-Fi have the like it do the beaconing. In beacon have the you will everything like SSID, then other information. So why not that whether the internet connectivity is available or not, and if it is available, that what is the latency and what is the what is the latency and what is the speed it provides. So you find that access point have all the information. You will find that there is a light for the internet, that is go when there is no internet on your access point, it goes red. So they have all the information. They run some, like you put if your Airtel access point is there, it also connect to their background server, and it check the latency and the other thing also. So they have all the information. So we append all the information into the beacon frame, and then later that our station, your mobile phone, that it know it that particular don't have not have an internet, and if it have the internet also, like what is the speed and what is the latency. For example, in my college I play lots of Counter Strike and other games, so that latency that time is more important in comparison of internet. So I also connect to the correct AP. That is a very simple, again simple patent, but it's very useful. So point is if you go to the just search for a use case, just search for your problem and you will get a useful patent idea. So I'm concluding my, it's a long presentation. So why Wi-Fi can consider as a best protocol for IoT development, and Wi-Fi 6 start this era for IoT. Earlier that Wi-Fi was not beneficial for IoT, but it's now. How MLO offers significant advantages, and how this real time and latency can problem solve using the MLO. That is so some future trend, like still Wi-Fi is taking more power, and compare if you compare with BLE, even ultra wideband or something. So that still need to solve. So as much as there is always there is always space for improvement. So you guys can work on this, still work on power reduction thing. How can you can reduce power for smaller devices? Protocol interoperability. So Wi-Fi protocol can work on different uh, other protocol like BLE, ZigBee, and other thing. Machine learning algorithm always for MLO management, you can you can do load balancing you the uh, for the MLO. Currently we check only this RSSI and other things, but you can analyze the pattern and check that how this MLO management can improve. Multi-AP coordination. Currently MLO is working with their AP only working with their devices, but it can also coordinate with multi-AP. Security and privacy is always there is a space. And MLO for legacy, like old network integration and energy efficiency with MLO, specific to MLO in case of STR or other mode. So these are future trend, and be ready. So if so much semiconductor works come, so there is always need of device driver and firmware developer, which can be shorter in future. So be ready with that, so people know, understand the things how embedded software or works. So ready for that. So that's all from my side. You guys have any question you can put. These are some references I use. So IEEE, Wi-Fi Alliance, Silicon Lab, there is a company which mostly work on the IoT things, on Wi-Fi 6 things, MediaTek, ARM developer guides, and something. Thank you.
Thank you so much, sir. There is one doubt from
Sure,
Mr.
sure.
Nagarajan in the
Uh,
chat box. I am reading for you. How
sure, sure.
might the adoption of Wi-Fi 6/7 impact the cost effectiveness of deploying large-scale IoT networks?
So if you talk about the cost, so for example, uh, if you see your access point currently, whether you are in university or you are home, you will find that Wi-Fi 5 or Wi-Fi 6 AP is there, not the Wi-Fi 7 AP. And you can check the Wi-Fi 7 AP cost on the internet. So depend, like Wi-Fi 6 is cheaper because it's a older generation in comparison of Wi-Fi 7. And I already covered like Wi-Fi this like. So what is your use case? Where you want to deploy? So whether it's a large scale, what your device like, it's a low power device, low bandwidth you need just for the smart sensor, wearable, your Google Home, Alexa, smart lights. These are connected. Go for the Wi-Fi 6. That would be the best for cost as for a cost. And if you are developing something big like for the smart city, robotics, industrial IoT, where that cost is not such a problem, go for Wi-Fi 7. Oops. Sorry.
So thank you, sir. It's fine.
Okay.
There is one other question. How do target wake time TWT features in Wi-Fi 6 contribute to energy savings for IoT devices, particularly in battery constrained environments?
So like a battery constant devices, so that's TWT negotiation can also done by the, like station side or access point device side. So if access point like understand like how much time you need to awake. For example, you are reading the heartbeat. So maybe in 1 minute, some second, 30 second, you need that data. But there is a like some data is, for example, like soil, humidity and other things that is not required in that particular time. So that TWT that duration you can set according to the your requirement. So whether your device is battery constrained devices. So lots of things also come into the play. How much battery is there? Even one in IoT network, if one device is taking lots of battery, so you can jump to the other device. The data can transfer to the by other device. So it's completely on your use case.
So I think it is well answered. Any other queries? Okay. There is one more query from the same participant. How do the features like OFDMA, orthogonal frequency division multiplexes, and MU-MIMO, multi-user, multi-input, multi-output in Wi-Fi 6 enhance IoT device efficiency and communication?
Okay. So let me explain in why a simple like there is a for example 4 devices connected and they are using 160 megahertz frequency. Okay. So I'm not talking about that sub carrier or other things. So I'm just simple taking simple example. There is a like 160 megahertz bandwidth is there. So currently in scenario that 40 megahertz is using by the user one, 40 megahertz is using by the user two, 40 megahertz by third and fourth.
I guess the question has been answered. So, any other questions? Okay. One more last question, sir, from the same participant. If you allow, shall I read for you? Dr. Bhargava? I guess there is some either network glitch or some power failure at his laptop. So let's wait for a few minutes if he comes back. Okay, he's back. So
Sorry,
Dr. Bhargava, it's okay, sir. I understand sometimes power failure occurs. So I guess you have
I maybe I can answer last question. If still.
okay. So the one more last question is what improvements does Wi-Fi 6E and future iterations bring to reduce interference in dense IoT ecosystems, especially in smart cities? That is the last question, I guess.
Okay. So like Wi-Fi 6, sorry, something is wrong with my machine. So Wi-Fi 6E means that there is a 6 gigahertz frequency also came. Okay. So Wi-Fi 6 gigahertz frequency all comes, so it have less interference. So whether it's into the dense IoT environment, but that 6 gigahertz have less frequency. And we are talked about the OFDMA. So that multiple RU, like a different station or different user can work, can divide that subcarrier resource unit. So that can optimize in a way like that if still my screen is not share, right? So if you remember that diagram, I show that on channel 1 that multiple user can work on that. So AP can manage in that way and divide into the group. So divide the station or the users into the group so that it increase the maximum efficiency. For example, like three station is three station can come into the group one, that what AP can manage that their data is limited, and one station is have very high data, so it can go into the group 2. So that's how that channel can divide in a way, so to increase the maximize usage of channels and the less interference. Is it am I answer?
Yes, I guess you have answered it very well, and hopefully the participant has got the satisfactory answer. So I guess we are done with the questions, and if there is anything else, we will connect you back. So
Okay.
I officially thank you, sir, on the
Thank you.
behalf of entire organizing committee and from my institute. We sincerely appreciate your time and effort that you dedicated to the session. And I feel that your talk was very informative and very motivating. So thank you so very much, sir. And we will look forward to attend more sessions from you in future. So thank you so very much, sir.
Thank you, Dr. Soumya.
Okay, sir.
And if any student wants to work on this Wi-Fi and embedded things, he can contact me. I just put my email ID in last slide. Okay.
Your screen is not shared. So it's better if you can drop your email ID in the chat box. It will be available to all the participants. Or
Sure.
we can do one another thing, sir. You share with either Arvind Dhaka, sir, or Lal Pratap, sir. We will share with
Okay.
the
Okay.
participants.
Sure. I will share with Arvind, sir. Thank you.
Okay, sir. Okay. And thank you so much, sir, for your time.
Okay. Thank you. Thank you very much. Thank you.
Okay, sir.
Bye.
Bye-bye, sir. Bye-bye.
Bye. Bye.